Nothing. At first it sounds simple, but defining it turns out to be quite complicated. Our universe began from what seems to be nothing, but what does it really mean? Is there a state where truly nothing exists? Or does nothing itself have some kind of hidden existence? A background from which something could appear? And where did nothing come from? Long before modern science tried to explain the mysteries of the universe, ancient thinkers were already asking some of the deepest questions. What does it mean to exist? Could there ever be such a thing as nothing? One of the earliest and most influential philosophers to tackle this idea was Parmenides of ancient Greece. He had a bold and mind-bending belief: nothing cannot exist. To him, the very idea of nothing was a contradiction. If something truly did not exist, how could we even think about it, let alone describe it? According to Parmenides, existence had no beginning and no end. It simply always was. He argued that the universe was eternal, unchanging, and never created. Because if there had ever been a time when there was absolutely nothing, how could anything have ever come into existence? His perspective forces us to rethink our assumptions. If nothingness is impossible, does that mean the universe has existed forever in some form? But not everyone agreed with him. Even in his time, other great minds wrestled with this paradox. Aristotle, another legendary philosopher, had a different view. He didn't see nothingness as a contradiction, but rather as a kind of potential, a blank slate where new things could emerge. Imagine an empty canvas before an artist picks up their brush. To Aristotle, this emptiness wasn't truly nothing. It was full of possibilities, a foundation for creation. He believed that even if space seemed empty, it still held the potential for things to exist. For centuries, philosophers and scientists have continued to debate these ideas. Can true nothingness ever exist? If the universe came from nothing, what kind of nothing are we talking about? These are questions that push the limits of human thought and force us to reconsider everything we think we know about reality itself. In more recent times, thinkers like Immanuel Kant began questioning the limits of human understanding. He asked a profound question: could nothingness, the complete absence of everything, be something our minds simply cannot grasp? Our entire existence is based on a world full of things: matter, space, time, things we can touch, feel, and measure. But Kant argued that true nothingness, where absolutely nothing exists, is beyond our ability to imagine or even understand. It's a concept so alien to our everyday experience that it feels like something that doesn't belong in our world of reality. Now this brings us to a deep and fundamental question. Could it be that nothingness, in its absolute sense, doesn't actually exist? Or is it possible that what we call nothing is actually the very source of everything around us, the spark that ignites creation? These are the types of questions that have puzzled some of the greatest minds throughout history, leading to one of the biggest mysteries of all: the birth of the universe. If we jump ahead a few thousand years, our understanding of nothingness has drastically changed. While philosophers were lost in these deep, mind-bending debates, science was quietly digging away, using tools like mathematics and experiments to uncover the truths of the universe. And this is where things get even more interesting. For centuries, scientists believed that space, the vast expanse where nothing seemed to exist, was exactly that: nothing. A vacuum was thought of as the absence of all matter. In this view, the universe's empty regions were, well, empty. No particles, no energy, just a blank, featureless space where nothing could possibly happen. But something amazing happened when the 20th century arrived, forever changing our understanding of what nothing actually means. The groundbreaking work of Albert Einstein brought about a shift in our understanding of the universe with his theory of general relativity. He showed that space and time weren't separate, but were instead connected, forming a kind of flexible fabric. This fabric could bend and stretch like a piece of cloth in response to the presence of mass and energy. This was an incredibly revolutionary idea. It meant that space wasn't just a backdrop where events occurred. It was active, dynamic, and played a significant role in shaping the events of the universe. But it didn't stop there. The real transformation in our understanding of nothingness occurred with the advent of quantum mechanics, a branch of physics that deals with the tiniest building blocks of the universe. It revealed something truly bizarre. Even in the emptiest parts of space, where nothing appears to exist, something is still going on. Imagine a perfect vacuum, a place completely devoid of matter, light, or anything we think of as something. Yet, even in this seemingly empty space, something is happening all the time. It's not a loud or obvious event, but it's there nonetheless. This something is known as quantum fluctuations, tiny, fleeting bursts of energy that pop into existence and vanish just as quickly. It's as if, on the smallest scale, the universe is constantly buzzing with activity, even when it looks completely still. These quantum fluctuations are incredibly fast and tiny, so much so that we can't see them with our naked eyes. However, even though we can't directly observe them, we can measure their effects. They are a real, quantifiable phenomenon. It turns out that even in what we think of as empty space, there are still invisible fields at work. These fields are constantly fluctuating like waves in the ocean, creating tiny particles that come into being and then disappear in the blink of an eye. These particles are called virtual particles, and although they last for only an extremely short time, they leave behind measurable traces of their existence. This idea of the vacuum being alive with potential might seem strange or even magical. After all, how can there be activity in a place that's supposed to have nothing? But this is the fascinating reality of the quantum world, where things never truly rest. Even in what seems like nothingness, there's always something moving, something fluctuating, something on the edge of existence. Now, this raises an incredibly interesting question. Could this constant bubbling of energy and particles be the key to the birth of everything? Could the entire universe have originated from one of these quantum fluctuations? A tiny burst of energy appearing out of nowhere, only to expand and become the vast cosmos we see today. This is one of the most mind-bending ideas in cosmology. If quantum fluctuations are capable of creating tiny bursts of energy in a vacuum, might they also explain how the entire universe could have come into existence from what seems like nothing? It's a concept that takes us into the very heart of the mystery of the universe's origins, challenging everything we thought we knew about nothing and everything. What if the entire universe we live in began because of a huge, dramatic shift on a cosmic scale? This brings us to a theory that has captured the imagination of scientists for many years: the Big Bang. It's the moment when everything we know, space, time, and matter, exploded into existence. But the real mystery is what caused this explosion. What could have triggered such an immense event that created everything in the universe? One of the most mind-boggling ideas comes from the strange and fascinating world of quantum physics. This theory suggests that the universe might have been born out of what scientists call a vacuum fluctuation. Imagine for a moment an empty, vast space, no stars, no planets, no galaxies, just a void. In this emptiness, out of absolutely nothing, a tiny burst of energy appears. It's incredibly small at first, but it grows quickly, rapidly expanding and creating everything around us: stars, galaxies, planets, and even the very space we move through. This idea proposes that the universe didn't just come from nothing. It came from a quantum event, a huge fluctuation that arose from what we once thought was empty, meaningless space. Before the Big Bang, this nothing wasn't as empty as we might think. Instead, it was full of quantum potential, just waiting for something to happen. It was like a hidden energy, a kind of cosmic seed, waiting to sprout into the vast universe we know today. As outlandish as this idea might seem, it's actually grounded in some of the most advanced scientific theories. Leading physicists, including the legendary Stephen Hawking and Lawrence Krauss, have explored this very possibility. Their research has shown that the strange laws of physics, especially the principles of quantum mechanics and gravity, might allow for the universe to arise from nothing without breaking any scientific laws. Stephen Hawking's work on the quantum origin of the universe suggested that space and time could emerge from what's called a quantum state. In this view, the universe didn't need a creator or a guiding hand to shape it in the way traditional religions describe. Instead, the universe could have created itself, following the rules of quantum physics. It's as if the universe unfolded naturally from the laws that govern the smallest particles, without needing anything outside of those rules to kickstart it. Lawrence Krauss expanded on this idea in his book a universe from nothing. He took it even further, suggesting that quantum fluctuations, the tiny, unpredictable movements that happen in the vacuum of space, could actually cause entire universes to appear. Just like how virtual particles pop in and out of existence in empty space, our entire universe could have been the result of one such fluctuation. From this perspective, the universe might have been born in an extraordinary, unlikely event where nothing gave rise to everything we know. The idea of nothing has always been a source of great mystery and fascination, both for philosophers and scientists. For centuries, we thought of nothing as just an empty, lifeless void, simply a blank space where there was no matter, no energy, and no activity at all. However, this idea of nothing is far more complicated and mind-boggling than it first seems. In philosophy, thinkers have long debated the idea of potential. This concept suggests that even in what seems like nothing, there is a hidden potential waiting to emerge. It's almost as if nothing isn't really empty, rather, it's a space full of possibilities. In the world of science, this idea takes on an even more fascinating form. Through the study of quantum physics, we now understand that even the emptiest, most seemingly void-like space is actually alive with tiny, energetic fluctuations. These fluctuations are so powerful that they have the potential to create entire universes. Imagine that. What we once thought of as an empty void is actually teeming with the energy and potential to form something as massive and complex as a whole new universe. While science and philosophy have given us these stunning, complex insights, the truth is, we may never fully grasp the true nature of nothing. But what is clear is that this mystery is far from trivial. It's one of the most intriguing puzzles of all. The more we think about it, the more we realize that the story of how everything came to be, the origin of everything we know, is just as incredible and mind-blowing as the universe itself. This concept of nothingness has captivated us for centuries. Ancient philosophers like the Greeks and the early thinkers of the East pondered its meaning, and now, modern scientists are uncovering even more unbelievable truths. From the quiet meditations of those ancient minds to the groundbreaking discoveries happening in labs today, the idea of nothing continues to hold us in awe. And as we gaze up at the night sky, filled with billions of stars and galaxies, we are reminded that the most extraordinary story of all may just be the one that begins with nothing. In the vastness of space, where we see the brilliance of stars and the swirling beauty of galaxies, it's humbling to remember that these wonders might have emerged from what seemed to be absolute emptiness. The universe, as we know it, could have come from nothing at all, and this idea, the possibility of creation from nothing, is what makes our universe and our place within it so fascinating and mysterious. Imagine for a moment that everything you see around you, the entire universe with its countless galaxies, stars, planets, and even the tiniest specks of dust, was once packed into a space so small that it was smaller than an atom. It's hard to believe, right? But this idea isn't just a scene from a science fiction movie, it's the basis of how our entire universe began. According to one of the most amazing theories in all of science, the Big Bang Theory, this is exactly how it all started. The Big Bang Theory is the most widely accepted explanation for how the universe came into existence. It tells the story of how everything, absolutely everything, from the stars in the sky to the atoms that make up everything we know, began from a single, incredibly tiny, infinitely dense point. This point was so small that it could hardly be imagined, yet it contained the potential for everything that would follow. From that single point, the universe we see today, vast, beautiful, and constantly expanding, emerged. But how did it all happen? What exactly was this bang, and how did it lead to the birth of the universe? Today, we're going to take you on an extraordinary journey back in time, almost 14 billion years ago, to the very moment when time and space themselves came into existence. Before the Big Bang, there was no universe, not as we understand it today. Imagine asking what came before the Big Bang. It's like asking for directions to a place north of the North Pole. There was no before in the traditional sense. There was no time, no space, and no matter. Everything we know and experience was packed into an incredibly hot and dense point, a concept scientists call a singularity. Picture this singularity as a point that held all the energy, all the matter, and all the potential for the universe, Everything we see today was contained in this unimaginably tiny space. Trying to picture this is almost impossible, but this singularity was the birthplace of everything. It was the seed from which the entire universe would grow. Then, around 13.8 billion years ago, something truly remarkable happened. For as long as time could be measured, there was nothing. No universe, no stars, no galaxies. And then, in an instant, there was everything. This tiny, dense singularity exploded in what we call the Big Bang. But don't think of it as an explosion like a bomb going off. The Big Bang wasn't an explosion in space, it was actually the sudden and rapid expansion of space itself. In a fraction of a second, space expanded from being smaller than an atom to something billions of times larger. This expansion didn't happen in a particular direction, it was space itself that stretched out, carrying everything with it. The Big Bang was the birth of time, space, and everything we know. But that was just the beginning. The real question is, what came next? How did that initial burst of energy, this incredible explosion of space, transform into galaxies, stars, planets, and all the things that make up the universe today? To understand that, we need to look at the timeline of events that unfolded after the Big Bang. From the first moments of the universe's birth, things began to cool down and take shape. Clouds of gas formed, stars ignited, and galaxies started to form, each one a massive collection of stars and other matter floating through the expanding universe. Over billions of years, these stars and galaxies evolved, creating the complex, diverse cosmos we see now. The journey from that tiny, hot point to the vast, sprawling universe we live in today is one of the most incredible stories of all time. To really understand how the universe evolved, we need to break it down moment, by the tiniest fractions of a second. In the early universe, a lot happened in almost no time at all, and it's crucial to zoom in on those brief but incredible moments to grasp how everything began. Let's start at the very beginning, at a time so early that it's hard to even imagine, during the Planck epoch. This first tiny fraction of time after the Big Bang, less than a trillionth of a second, was when the universe was in a state unlike anything we experience today. Picture the universe being extremely tiny and incredibly hot, hotter than anything we can comprehend, over a quadrillion degrees. In this intense and strange environment, all four of the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, were united into one single force. This is something that's hard for us to fully understand, because in our current world, those forces work independently. But back then, they were all part of one unified force. What does that mean? Essentially, during the Planck epoch, everything we know about the laws of physics, what we call science today, was merged into a single force. But here's the twist. We don't truly know what happened during this time. Our current laws of physics, like Einstein's theory of general relativity and quantum mechanics, both fall apart in this extreme environment. It's like trying to put together two puzzles where the pieces just don't fit. And this is where it gets tricky. We can't fully understand what occurred because these conditions were so far outside our normal experience that our best scientific theories just break down. What we do know is that during the Planck epoch, the universe was expanding incredibly fast. Imagine the space itself stretching out at an unbelievable speed. However, because the universe was so hot and dense at that time, there was no light. Everything was hidden in a kind of cosmic fog, making it impossible for us to look back and directly observe what was going on. So, what happened after that? Well, as the universe cooled, though cool is a relative term since it was still millions of times hotter than the core of the sun, things started to change. The first major shift was the separation of gravity from the other three forces. Gravity, which had once been unified with the other forces, now started acting on its own. This marks the beginning of what we call the Grand Unification Epoch. During this time, the remaining forces, electromagnetism, the strong nuclear force, and the weak nuclear force, continued to stay together, but gravity began to pull away. The universe is an ever-changing, dynamic place, and its expansion has been an incredibly important event in the story of our existence. Right after the Big Bang, something surprising happened. The expansion of the universe slowed down just a little bit, but that wasn't the real game changer. No, the real surprise was still to come, and it would change everything forever. About 1/septillionth of a second after the Big Bang, the universe experienced an event known as inflation. This wasn't just a small change. It was an explosive, rapid expansion that stretched the universe at an unimaginable speed, much faster than the speed of light. Yes, faster than light itself. This mind-boggling speed caused the universe to grow from the size of an atom to billions of times larger almost instantly. Imagine something so vast expanding in a fraction of a second. It's nearly impossible to wrap our heads around. So why did inflation happen? Well, that part is still a bit of a mystery. Scientists are not entirely sure, but many believe it was due to a special form of energy called the inflaton field. This energy was responsible for pushing space itself to stretch faster than light. If the universe was expanding so rapidly, that means space itself was growing, and that space was stretching out to create all the room for the stars, planets, and galaxies that would eventually appear. After this wild expansion, the universe began to cool down. As it cooled, the four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, started to separate from one another. Each force began to act independently, and this paved the way for matter to begin forming. As the universe continued to cool, the next significant step came with the formation of the first subatomic particles. Quarks and gluons were born. Quarks are the fundamental building blocks of protons and neutrons, and gluons are the particles that bind quarks together through the strong nuclear force. During this time, the universe was in what we call the quark epoch. It was an intense, chaotic time when particles were constantly crashing into each other, sometimes creating new particles and other times breaking apart. The heat was still incredibly high, so these particles couldn't stick together yet, but they were in the process of forming the matter that would one day become everything around us. The universe was still too hot for these particles to form anything stable, and everything was in a state of constant fluctuation. Think of it like a giant cosmic soup, where particles flickered in and out of existence at lightning speed. But as the universe continued to cool, the forces holding particles together grew stronger, and slowly, these tiny pieces of matter started sticking together. This was just the beginning of something much bigger. Now we have to talk about photons, tiny particles of light. About 10 seconds after the Big Bang, photons began to play an incredibly important role in shaping the universe. At that time, the universe was still full of free electrons and protons. These electrons were constantly bouncing off the photons, and as a result, the universe was opaque, like a thick fog where light couldn't travel very far without being stopped by one of these particles. However, over the next few minutes, something amazing happened. The first atomic nuclei began to form in a process called nucleosynthesis. Protons and neutrons combined to create the first nuclei of the lightest elements in the universe: hydrogen, helium, and a little bit of lithium. These elements were the first building blocks of matter, and they would eventually form stars, planets, and everything we see around us today. Let's take a journey through the universe's past, hundreds of thousands of years after the Big Bang. At this point, the universe had cooled down enough to allow electrons to join with protons and form neutral atoms. This event is called the Era of Recombination, and it marked a major turning point in the history of the universe. Up until that time, the universe was filled with a dense fog of hot, charged particles. But now, for the first time, it was clear enough for light to travel freely. Previously, light had been trapped, constantly bouncing off particles. Now it could finally travel unimpeded, spreading out across the universe. This momentous change left behind something very important, one of the most significant pieces of evidence for the Big Bang, the cosmic microwave background radiation, CMB. The CMB is a faint glow of leftover heat from the Big Bang itself, and it's still detectable today. Even though the universe has cooled down enormously since the Big Bang, that early heat lingers in the form of the CMB like a cosmic echo. This glow allows scientists to study what the universe looked like when it was just 380,000 years old. But you might be wondering, how do we know all of this for sure? How can we be confident in the Big Bang theory? Well, the Big Bang theory isn't just a wild guess or an idea pulled out of nowhere. It's backed by a lot of solid evidence. Let's dive into 3 key pieces of evidence that make the Big Bang theory the most widely accepted explanation for the origin of the universe. First up, there's the cosmic microwave background radiation, CMB. The CMB is often referred to as the afterglow of the Big Bang. It's the leftover heat from the universe's birth, still detectable today. The CMB was first discovered in 1965 by scientists Arno Penzias and Robert Wilson. This discovery was a game changer. The CMB is like a snapshot of the universe when it was in its infancy, just 380,000 years old. At that time, the universe was a hot, dense plasma, glowing with intense heat. Over billions of years, that glow has cooled, but it's still out there, and we can detect it using special telescopes. The CMB is an incredibly important piece of evidence because it's a direct remnant of the Big Bang itself. What makes it even more powerful is that it's uniform across the sky, meaning it looks the same no matter where we look. This tells us that the universe began from a single, incredibly hot point, and over time it has expanded and cooled to what we see today. Next, we have the phenomenon known as redshift. When we look at distant galaxies, we notice that the light coming from them is stretched out, shifting toward the red end of the spectrum. This effect, called redshift, happens because the universe is expanding. As space itself stretches, it pulls on the light traveling through it, making the light appear redder. This was first noticed by the astronomer Edwin Hubble in the 1920s. Hubble discovered that galaxies are moving away from us, and the farther away they are, the faster they're moving. This was a huge clue that the universe itself is expanding. If the universe is expanding now, it must have been much smaller in the past. And this leads to the conclusion that the universe began from a single, incredibly dense point, the Big Bang. Finally, there's the abundance of light elements like hydrogen, helium, and lithium. In the very early universe, it was so hot and dense that nuclear fusion was happening all around. For a brief period, only the lightest elements could form. This process produced a lot of hydrogen and helium, and just a tiny bit of lithium. Today, scientists observe that the universe is made up of about 75% hydrogen and 25% helium, with only trace amounts of heavier elements. This matches the predictions made by the Big Bang theory, specifically the idea that the universe went through a hot, dense phase where these elements were created. The Big Bang theory tells a fascinating story about how the universe started. Imagine, billions of years ago, everything in existence, stars, planets, galaxies, and even the space around us, was packed into a tiny, super hot and dense point. This incredibly small and tightly packed point then exploded, marking the birth of the universe as we know it today. From this explosion, particles began to form, and slowly over time, these particles came together to create stars, galaxies, and everything in the universe. As time passed, the universe continued to expand. It didn't just stop growing after the initial explosion. Instead, it has been expanding and changing for billions of years. And even today, it's still stretching out, with space itself getting bigger all the time. Scientists believe that this process won't stop anytime soon. In fact, it might keep going for billions, even trillions of years into the future. The universe is like an ever-growing puzzle, and we're just beginning to understand how its pieces fit together. However, the Big Bang theory doesn't just explain how the universe began. It also leaves us with even more questions. While we have learned a lot about how the universe was formed, there are still many mysteries out there. As we continue to explore space, scientists are discovering new things that help piece together this massive, complex puzzle. Each discovery brings us closer to understanding not only how the universe started, but also how it might eventually end. From the tiniest particles that were formed in the first moments of the Big Bang to the largest galaxies that exist today, the story of the universe is vast and still unfolding. The Big Bang theory helps us peek into this incredible journey, from the very beginning to the endless future. It's like reading the first chapter of a book that has no ending in sight. The Big Bang is not just a moment in history, it's a story that's still being written, one discovery at a time. As we try to uncover the origins of our universe, we inevitably run into one of the greatest mysteries of modern science: the singularity, the strange point at the very heart of the Big Bang. Scientists believe that this singularity was the source from which everything, space, time, matter, and energy, emerged. But this raises an even bigger question: what came before the Big Bang? In simple terms, a singularity is a point where the laws of physics as we know them stop working. It's a place where matter is infinitely dense and gravitational forces become so strong that they distort space and time beyond comprehension. In such extreme conditions, even our most advanced equations, like Einstein's theory of general relativity, break down. This means that everything we currently understand about the universe cannot explain what happens inside a singularity. The singularity at the beginning of the universe was even more perplexing than the ones we find in black holes. Instead of being inside an object like a collapsing star, this singularity was the beginning of everything. At this moment, the universe was squeezed into a tiny, incredibly hot and dense point, a state where all known laws of physics collapsed. Then, in an instant, this singularity exploded outward, creating everything we see today in what we now call the Big Bang. But here's where the mystery deepens. If the Big Bang created space and time, what existed before time began? Asking what was before the Big Bang is tricky because it assumes that time itself existed before the universe. But according to Einstein's theory of relativity, time and space are connected. They are part of the same fabric called space-time. If the Big Bang created space-time, then time itself did not exist before the singularity. This means that the concept of before the Big Bang might be meaningless. However, some physicists believe there might be more to the story. Theoretical models suggest several possibilities. Some theories propose that our universe didn't actually start from nothing, but instead follows an infinite cycle of expansion and collapse. According to this idea, the universe expands, reaches a peak, then contracts back into a singularity, only to explode again in another Big Bang. This endless cycle of birth, death, and rebirth could mean that something always existed before our current universe. Another possibility comes from quantum mechanics, the strange science that governs subatomic particles. Quantum physics suggests that tiny particles constantly pop in and out of existence, even in the vacuum of space. Some physicists propose that the entire universe might have emerged from a quantum fluctuation in an empty void, meaning that before the Big Bang, there was simply a vast emptiness with strange, unpredictable quantum activity. Some scientists speculate that our universe is just one of many universes, part of an enormous multiverse. According to this theory, universes are constantly being created in an infinite cosmic sea. If this is true, then something always existed before our universe. It was simply another universe, or a different state of existence altogether. In the 1970s, Stephen Hawking and Roger Penrose made groundbreaking discoveries about singularities. They combined Einstein's theory of general relativity with the strange rules of quantum mechanics, leading to new insights into how singularities work. Their research showed that singularities are not just a theoretical idea, but an inevitable reality under certain conditions, like the beginning of the universe or the center of a black hole. Hawking and Penrose proved that if you rewind time to the very start of the universe, you reach a moment where the curvature of space becomes infinite, a point where time and space cease to behave normally. This means that before the Big Bang, there was no recognizable space, no flow of time, just an incomprehensible state of infinite density. Science has given us incredible insights into the first moments of the universe, but the moment before the Big Bang remains one of the greatest unsolved mysteries. Since time itself may have started with the Big Bang, some physicists argue that the question of before might not even make sense. Others believe that we just haven't yet discovered the right laws of physics to explain it. In our daily lives, time feels like an unstoppable river, constantly flowing from one moment to the next. If you think back, you can always ask what happened before, yesterday, last year, or even 1,000 years ago. This seems like a natural way to understand time. However, when we try to apply this logic to the very beginning of the universe, things become much more complicated. At the heart of this puzzle is the concept of the singularity, a moment when all known laws of physics break down. Some scientists believe that time itself might have started at the moment of the Big Bang, meaning there was no before at all. Asking what happened before the Big Bang would be like asking what lies north of the North Pole. There simply is no direction beyond that point. This idea suggests that time, as we know it, only exists within the universe and did not exist before it. However, not all scientists agree with this view. Some propose that the singularity might have come from something that existed earlier. Perhaps the universe emerged from quantum fluctuations in an empty vacuum, a process where tiny, unpredictable changes in energy could have triggered the birth of everything. Others suggest that our universe might be just one in a series of cyclic universes, where a previous universe collapsed and then gave rise to the Big Bang. While these theories are highly speculative and push the limits of our scientific understanding, they offer fascinating possibilities about what might exist beyond what we can observe. One of the most famous physicists to explore these ideas was Stephen Hawking, who spent much of his career studying black holes, objects in space where gravity is so powerful that nothing, not even light, can escape. Interestingly, black holes have a singularity at their core, much like the singularity thought to exist at the birth of the universe. This means that by studying black holes, scientists can gain clues about what might have happened at the very beginning of time. In a groundbreaking discovery, Hawking found that black holes are not completely dark as previously thought. Instead, they emit faint energy known as Hawking radiation, which suggests that black holes can slowly lose mass and eventually evaporate over time. This was a shocking idea because it challenged the belief that anything swallowed by a black hole was lost forever. It also raised deeper questions about the nature of information in the universe. Does information truly vanish, or is there some unknown way it could be preserved? The study of singularities, whether in black holes or the Big Bang, reveals a fundamental problem in modern physics. Our two most powerful theories, Einstein's general relativity, which explains gravity and large-scale cosmic structures, and quantum mechanics, which governs the tiny world of subatomic particles, do not work well together. In the extreme conditions of a singularity, these theories break down, leaving scientists searching for a better explanation. Many physicists believe that the missing piece of the puzzle is a theory called quantum gravity, which would merge relativity and quantum mechanics into one unified framework. If such a theory were discovered, it could help us understand what happens inside a black hole, what truly occurred at the Big Bang, and whether anything existed before it. For many years, scientists have tried to create a complete and tested theory that connects quantum mechanics and gravity, two of the most fundamental forces in the universe. However, despite countless theories and mathematical models, no one has been able to fully prove how gravity works on the smallest quantum level. This mystery makes it difficult to understand one of the most important moments in cosmic history, the singularity at the beginning of the Big Bang. Singularity is not just the starting point of our universe, it is also a boundary that limits our current knowledge. It marks the moment when time, space, and matter first emerged, yet it also represents a wall that science has yet to break through. Our everyday experience of reality is based on familiar concepts like cause and effect, space having 3 dimensions, and time moving in a straight line. But the singularity challenges all of these ideas. It forces us to consider possibilities that go beyond what we can see, measure, or even fully imagine. What if the laws of physics as we know them only apply after the Big Bang and not before? What if time itself didn't exist in the way we understand before that moment? This search for answers brings us back to some of the deepest and oldest philosophical questions in human history. What is existence? How did something come from nothing? Can we ever truly comprehend the exact instant when the universe was born? These questions have fascinated thinkers for thousands of years, from ancient philosophers to modern scientists, and they remain at the heart of our quest for knowledge. As technology advances and new discoveries are made, we continue to push the boundaries of what we know about the universe. Telescopes peer further into space, particle colliders reveal the tiniest building blocks of reality, and theories attempt to weave together the vast and the minuscule into a single unified understanding. Yet, the singularity remains a mystery, an enigma that challenges us to think beyond everything we currently understand. It stands as both an invitation and a challenge, urging us to explore the deepest mysteries of the cosmos and the very nature of reality itself. Let's dive deep into a fascinating idea known as cosmic inflation, an incredible event that occurred right after the Big Bang and shaped everything we know today. Imagine the universe just moments after the Big Bang. It was unimaginably small, super hot, and expanding at a speed beyond anything we could ever comprehend. Now picture this. In the blink of an eye, the universe expanded faster than the speed of light. a phenomenon so mind-boggling that it changed everything in the universe. This rapid expansion is what scientists call cosmic inflation. It's one of the most exciting and challenging ideas in all of cosmology because it explains how our universe went from being an almost invisible speck of matter to the vast, organized cosmos we observe today. Without this theory, many aspects of the universe wouldn't make sense at all. To fully grasp inflation, we need to take a step back in time, way back, to just after the Big Bang. Picture this moment, known as Planck time, which occurred around 1 quatuor-decillionth of a second after the Big Bang. At this point, the universe was tiny, so small that it might have been smaller than a proton. But then, something extraordinary happened. In an incredibly short amount of time, the universe began to grow at an astonishing rate. This is where the story of cosmic inflation begins. Cosmic inflation is the idea that in the first few fractions of a second after the Big Bang, specifically between 1 tridecillionth of a second and 1 billionth of a second, the universe expanded at a mind-blowing pace. During this period, the universe grew exponentially. To put this into perspective, imagine taking something as small as an atom and stretching it out to the size of an entire galaxy in less time than it takes to blink. That's the power of inflation. It made the universe grow by a factor of at least 100 quintillion. Now, don't mistake this for an explosion. This wasn't like fireworks or matter flying apart in all directions. Instead, it was space itself stretching and growing. The space between galaxies, stars, and particles expanded faster than light, and although this sounds impossible, it is actually allowed by the laws of physics. Because it's not matter traveling faster than light, it's the space itself that's expanding. And space, as strange as it may seem, doesn't have the same limits that objects moving through space do. Inflation did more than just rapidly expand the universe. It helped solve some of the biggest mysteries in cosmology, things that would otherwise be difficult to explain. For example, if you take a look at the night sky, the stars may seem scattered randomly across the universe, but if you zoom out far enough and take a broader look, you'll see something strange. No matter where you look, the universe seems more or less the same. The cosmic microwave background radiation, the faint glow left over from the Big Bang, is almost exactly the same temperature everywhere you look. This is where things get intriguing. You might think that the universe, if it started from an extremely hot, dense point, should have regions that are very different from each other, especially when those regions are billions of light years apart. How could two far-off parts of the universe be so similar in temperature and structure? This is a mystery known as the horizon problem. According to the standard Big Bang model, there hasn't been enough time for light or heat to travel between these distant regions to even them out. Without inflation, these far-off regions should look quite different, with some areas much hotter or colder than others. But inflation solves this puzzle. By stretching space so rapidly, it allowed distant regions to be in contact with each other in a way that evened out the temperature and distribution of matter. During a period of inflation, the universe expanded at an incredibly rapid rate. This rapid stretching was so extreme that regions of space that were once close to one another were stretched far apart. Imagine this. Before inflation, all parts of the universe were connected, like different sections of a crowded room. They shared the same temperature and conditions, and that's why even today, no matter how far apart different regions of space are, they look very similar. This rapid expansion of the universe also helped smooth out any early irregularities. Picture a balloon with little bumps all over it. If you inflate that balloon really quickly, those tiny bumps get stretched out and smooth over, right? Well, that's similar to what inflation did for the universe. It took a universe full of small irregularities, tiny wrinkles in space, and stretched them so far apart that they became smooth and uniform. Not only did inflation make the universe more uniform, but it also gave us clues about how galaxies and stars formed. The rapid expansion of the universe helped set the stage for what we see today. Clusters of galaxies, stars, and planets all spread across space. But you might be wondering, that sounds fascinating, but is there any proof that inflation actually happened? And that's where it gets even more interesting. While inflation is still considered a theory, there's a lot of strong evidence to support it. A big piece of this evidence comes from something known as the cosmic microwave background, CMB, the earliest light we can detect from the universe. Scientists study the CMB to understand what the early universe was like, and it's in these ancient light waves that we find important clues about inflation. One of the most important predictions of inflation theory is that there were tiny fluctuations, microscopic ripples in space and time, happening during the rapid expansion. Even though the universe was expanding quickly, these tiny fluctuations, known as quantum fluctuations, still occurred. They were small, but as the universe grew, these fluctuations stretched out to become large enough to influence the formation of galaxies, stars, and planets. Over time, these fluctuations left an imprint on the cosmic microwave background. When scientists look closely at the CMB, they can spot tiny temperature variations, which are the leftover signs of those early fluctuations. Without inflation, these variations would be much bigger or may not exist at all. But because the predictions from inflation match what we observe in the CMB so closely, it's like finding a fingerprint left behind by the early universe, showing us that inflation really took place. But that's not all. There's another mystery that inflation helps to solve: the flatness of the universe. When scientists study the overall shape of the universe, they find that it's almost perfectly flat. By flat, we don't mean it's like a flat piece of paper. Instead, it means that space isn't curved or bent like a ball or stretched out like a saddle. Space seems to follow the rules of ordinary flat geometry, even when we look at the largest scales. Now here's the puzzling part. If the universe had started randomly, it would have likely been either curved or warped in some way. So how did it become so flat? This is where inflation comes in. The universe expanded so quickly that on the largest scales, it became nearly perfectly flat. When we measure the geometry of the universe today, we find that it is indeed flat, just as inflation predicted. Let's take a closer look at how inflation played a critical role in the creation of galaxies and the structure of the entire universe. We've already touched on the concept of tiny quantum fluctuations, those tiny, almost invisible ripples that existed in the early universe. These fluctuations weren't just random noise, they were actually key to the formation of everything we see today. During the period of inflation, these tiny ripples in the fabric of space were stretched across the entire universe in an instant. It's like stretching out a tiny piece of fabric to cover an entire room in the blink of an eye. Over time, these fluctuations began to grow larger, and as the universe continued to cool, they formed the first tiny clumps of matter. As the universe cooled further, these clumps of matter began to collapse under their own gravity. It was this process that eventually led to the formation of the very first stars and galaxies. This is how the large-scale structure of the universe began to take shape. The way galaxies are spread out across vast distances in clusters and long, intricate filaments actually matches what we would expect if inflation occurred. The tiny ripples from that early inflation were the seeds that grew into the galaxies and stars we see today. So, when we look at the vast cosmic web of galaxies stretching across the universe, we are seeing the direct result of those tiny initial fluctuations that were stretched out during inflation. Without inflation, it's hard to explain how the universe developed this particular structure. The way galaxies are positioned today, how they form clusters, and how they're connected by vast filaments, it all fits perfectly with the idea of inflation. Inflation didn't just help form the galaxies, it also explains the uniformity of the universe while still allowing for tiny imperfections. These imperfections, though minuscule at first, slowly grew into the stars, galaxies, and everything we know in the universe today. So, what exactly is cosmic inflation? Imagine the universe in the first split second of its existence, before galaxies, stars, or even atoms could form. In that moment, the universe expanded at a mind-boggling speed, faster than we could possibly imagine. This expansion happened in the blink of an eye, setting everything in motion that led to the universe we know now. Inflation is the process that explains how the universe grew so large, so flat, and so uniform in the beginning. But it didn't just create uniformity, it also gave rise to the small variations that would eventually develop into galaxies and stars. Even though inflation is still considered a theory, there is strong evidence supporting it. We can see its fingerprints everywhere, from the cosmic microwave background, the afterglow of the Big Bang, to the large-scale structure of the universe. All around us, there are traces of that ancient inflationary event. It's a reminder that, right from the very beginning, Powerful cosmic forces were already shaping the universe, preparing the way for everything that came afterward. Inflation stands as one of the biggest achievements of modern cosmology. It helps us understand how the universe, which started from an incredibly tiny and dense point, expanded into the vast, complex cosmos we live in today. As we continue to explore space and uncover more about the origins of the universe, we'll discover even more secrets about how everything began. But for now, we can marvel at the fact that in the first fraction of a second, the universe expanded faster than anything we could have imagined. And that very expansion is the reason we're here today, able to gaze up at the stars. Everything we see around us, every star, every planet, every galaxy, and even the tiny atoms that make up our bodies, was once packed into an unimaginably small space, even smaller than a single atom. Then, in a moment of incredible force, the Big Bang occurred, and the universe burst into existence. But that raises a fascinating question. How did this explosion of pure energy transform into the solid matter that makes up our universe today? This is the incredible story of how everything, planets, stars, and even life itself, came to be. It's a tale of invisible particles, their mysterious opposites called anti-particles, and a grand cosmic battle that determined the fate of everything we know. In the very first fractions of a second after the Big Bang, the universe was unimaginably hot and dense, so extreme that ordinary matter simply couldn't exist. Instead, it was a chaotic, seething ocean of energy. But as the universe rapidly expanded, something astonishing happened. That energy began turning into tiny particles. You might recall Einstein's famous equation, energy equals mass times the speed of light squared, E equals sine mc2, which tells us that energy can become matter. That's exactly what was happening. But there was a catch. Whenever a particle appeared, a mirror image version of it, called an antiparticle, appeared as well. Imagine it like a cosmic game of twinning. For every proton, there was an antiproton. For every electron, a positron. These antiparticles were nearly identical to their regular counterparts, except for one major difference. They carried the opposite electric charge. But there was a problem. Whenever a particle and its antiparticle met, they annihilated each other, disappearing in a flash of pure energy. This was happening constantly, filling the early universe with an intense battle of creation and destruction. With particles and antiparticles cancelling each other out, how did anything survive? Why wasn't the universe left completely empty, with nothing but light? This leads to one of the biggest mysteries in physics. Why does matter exist at all? In a perfectly balanced universe, every bit of matter should have been wiped out by its antiparticle, leaving behind a universe of nothingness. And yet here we are, surrounded by planets, stars, and galaxies. So what tipped the scales? Scientists believe that in those first moments of existence, nature played a tiny trick, an almost imperceptible imbalance. For every billion antiparticles, there were just 1,000,001,000 particles of matter. That minuscule difference, that one extra particle in 1,000,000,000, was enough to ensure that when the rest of matter and antimatter annihilate each other, a tiny amount of matter remains. And that tiny leftover amount, that's everything we see in the universe today. Every star, every galaxy, every planet, and every living thing, including us, is here because of a small imperfection in the early universe. If that slight imbalance had never happened, nothing, absolutely nothing, would exist. But even after matter won its battle for survival, the universe was still just a swirling sea of individual particles. So how did those particles come together to form the first atoms, the fundamental building blocks of everything we know? In order to truly understand how the universe evolved, we need to explore one of the most critical moments in its history, the birth of the first elements. This event, known as nucleosynthesis, was a turning point that set the stage for everything we see in the cosmos today. In the very first moments after the Big Bang, the universe was an unimaginably hot and dense place, filled with a chaotic sea of tiny particles. These particles, protons, neutrons, electrons, and others, were colliding at extreme speeds, unable to come together in a stable form. But as the universe expanded, it also began to cool. Just a few minutes after the Big Bang, temperatures had dropped enough for something extraordinary to happen. The free-floating protons and neutrons finally had a chance to fuse together, forming the very first atomic nuclei. This process, called nucleosynthesis, was the first step in the formation of matter as we know it. The intense energy of the early universe allowed protons and neutrons to combine through nuclear fusion, creating the nuclei of the first elements. However, because the universe was still extremely hot, only the lightest elements could form. Within just a few minutes, three primary elements emerged. Hydrogen, the simplest and most abundant element in the universe. It formed when a single proton attracted an electron, creating a stable hydrogen atom. Hydrogen would go on to be the primary fuel for stars. Helium, the second most common element. It formed when two protons and two neutrons fused together, creating a nucleus strong enough to hold electrons in orbit. Lithium, a rare element that was produced only in trace amounts. Though it was present in small quantities, lithium would later play an important role in the formation of certain types of stars and planets. These three elements, hydrogen, helium, and lithium, made up nearly all the matter in the early universe. There were no heavier elements yet, no carbon, oxygen, or iron, the essential ingredients for planets, life, and everything we see today. Even though these elements were produced in great abundance, the universe remained mostly empty. At this stage, there were no stars, no galaxies, and no planets, just vast clouds of hydrogen and helium floating through space. It would take hundreds of millions of years for these simple atoms to come together under the force of gravity, forming the first stars. These stars would later act as cosmic factories, creating heavier elements deep within their fiery cores and spreading them across the universe through powerful explosions called supernovae. The birth of the first elements was a crucial milestone in the universe's journey toward complexity. Without hydrogen and helium, there would be no stars. Without stars, there would be no heavier elements like carbon, oxygen, or iron, elements that make up planets, water, and even life itself. Even today, hydrogen remains the most abundant element in the cosmos, making up about 75% of all visible matter. Helium accounts for most of the remaining 25%. Together, these two elements continue to fuel stars, shaping the universe in ways that began billions of years ago. But back in those early days, the universe was still young, still expanding, and still cooling. The simple atoms that had just formed were waiting for gravity to take hold, waiting to come together, waiting for the moment when the first stars would finally ignite, bringing light to the darkness of space. The birth of the universe was nothing short of extraordinary. In the very beginning, the cosmos was a swirling sea of energy where tiny particles and their opposites, antiparticles, flashed in and out of existence. It was a chaotic dance, with particles constantly colliding and annihilating each other. But somehow, matter gained the upper hand over antimatter, a mysterious imbalance that shaped everything we see today. Without this slight edge, the universe as we know it, galaxies, stars, planets, and even life, would never have formed. Once matter became dominant, the next step in the cosmic story began. In a process known as nucleosynthesis, the first simple elements, hydrogen and helium, were created. These were the building blocks of everything that would come later. But in those early days, the universe was still a dark, empty place. There were no stars, no planets, just an expanding sea of gas. As time passed, gravity began to pull hydrogen and helium together, forming dense clouds. In some regions, these clouds became so compact that the pressure and heat triggered nuclear fusion, the same process that powers the sun today. This was the birth of the first stars, massive, glowing spheres of burning gas. As these first stars ignited, the universe lit up for the first time, marking the end of the cosmic dark ages. These first stars weren't just sources of light, they were also the factories of creation. Inside their fiery cores, nuclear reactions forged heavier elements, including carbon, oxygen, iron, and many others, the essential ingredients for planets, oceans, and even life itself. But these stars were short-lived. When they exploded in supernovae, they scattered these newly created elements across the universe, enriching space with the raw materials needed for the next generation of stars and planets. With more heavy elements in existence, new stars formed, surrounded by swirling disks of dust and gas. Over millions of years, these particles clumped together to create planets, moons, and asteroids. Some planets, like Earth, developed atmospheres and oceans, setting the stage for the emergence of life. Every atom in your body, whether it's the oxygen you breathe, the calcium in your bones, or the iron in your blood, was once part of a distant star that lived and died billions of years ago. The story of the universe is the story of us, written across time in the language of stardust. But this is just the beginning. The universe is still evolving, with galaxies colliding, new stars forming, and planets continuing to take shape. As we explore further, uncovering the secrets of black holes, dark matter, and the possibility of life beyond Earth, we realize just how vast, complex, and breathtaking the cosmos truly is. When we look up at the night sky, we are greeted with a breathtaking display of stars. These tiny points of light sparkle and shine, scattered across the vast, dark canvas of space. But have you ever wondered how these stars came to be? How did they form from the cold emptiness of space? This is the incredible story of how stars are born, how they live, and how they eventually die in spectacular, fiery explosions that light up the universe. Stars are not just beautiful objects in the sky, they are the engines of the universe. Their energy fuels the creation of new elements, provides light to planets, and even helps shape the galaxies they call home. To understand how stars form, we need to start by looking at the places where they are born, the stellar nurseries or nebulae. These are enormous, dense clouds of gas and dust spread across the galaxy, some of which stretch for light years. They are like giant cradles, holding the building blocks of new stars. But these nebulae aren't just sitting still in space. Over millions of years, something remarkable begins to happen inside them. Gravity, the invisible force that pulls everything toward each other, starts to work its magic. Slowly, the gas and dust in the nebula begin to collapse under the weight of their own gravity. As this material falls inward, it gets hotter and denser, and the particles begin to collide and compress. This is when the birth of a star begins. Out of the chaos of gas and dust emerges a baby star, called a protostar. At this stage, the protostar isn't yet shining like the stars we see twinkling above us. It's still too cool, and it hasn't yet reached the temperatures necessary to start shining. But the process of becoming a full-fledged star has started. As the protostar continues to collapse, its core, right at the center, becomes denser and hotter. The pressure and heat build up until something extraordinary happens. Nuclear fusion ignites. This is the moment when a star is truly born. When the core of the protostar reaches temperatures of about 10 million degrees Celsius, the hydrogen atoms in the core begin to fuse together. This fusion process creates helium and releases an incredible amount of energy. This energy pushes outward with tremendous force, fighting against the pull of gravity, which is trying to collapse the star in on itself. This balance of forces, gravity pulling inward and the energy from nuclear fusion pushing outward, creates a stable, shining star. For millions, sometimes billions of years, the star will maintain this delicate balance. Gravity and fusion will continue to work against each other, keeping the star steady and stable. The fusion process creates the light and energy that we see, and this is what allows stars to shine brightly in the night sky. This constant tug-of-war between gravity and energy is the heart of a star's life, and it continues until the star reaches the end of its journey. But the life of a star doesn't last forever. Eventually, even the most powerful stars will run out of fuel and begin to die. The death of a star is just as spectacular as its birth, with massive explosions that scatter elements throughout space, helping to form new stars, planets, and even life. From the swirling gas clouds of stellar nurseries to the magnificent final explosions of dying stars, the journey of a star is a never-ending cycle of creation and destruction, a cosmic evolution that shapes the universe we live in. Stars are born in the chaotic beauty of nebulae, grow through a battle of forces, and end their lives in explosive displays of energy. This cycle of life from birth to death is what drives the universe forward, creating the elements that make up everything around us. Stars, though brilliant and beautiful, live lives that are far more complex than we often imagine. Their ultimate fate hinges heavily on one key factor, their mass. In this conversation, we'll dive into the incredible journeys of stars, exploring how their size determines how they live, age, and eventually die. Most stars spend the majority of their lives in a phase called the main sequence. This is the steady part of their lives, where they fuse hydrogen atoms into helium at their cores, releasing enormous amounts of energy in the process. This energy is what makes stars shine. Our own sun is a main sequence star, and it has been burning through hydrogen for about 4.6 billion years. However, the mass of a star is incredibly important when it comes to how long it stays in this stable phase. Smaller stars, known as red dwarfs, burn their fuel much slower. They are not in any rush, so they can shine for an incredibly long time, trillions of years in fact. This gives them a slow and steady existence. On the other hand, larger stars burn through their fuel much faster. They live fast and die young. A large star, like a massive blue giant, only has a few million years to live before it uses up all its hydrogen. Once that happens, something major happens. What happens next depends on the star's mass, and here the future of the star splits into two very different paths. For stars like our Sun, which are of low to medium mass, their death is much gentler. When these stars run out of hydrogen to burn, they undergo a dramatic transformation. Their cores, under the intense force of gravity, start to shrink, while their outer layers expand massively. This expansion causes the star to become a red giant, a huge and swollen version of its former self. During this phase, the star sheds its outer layers into space, creating a stunning cloud of gas and dust known as a planetary nebula. All that remains of the star is its hot, dense core. Over time, this core cools and fades, turning into a white dwarf. Despite being roughly the size of Earth, a white dwarf can be incredibly dense, packing the mass of the Sun into a small, compact space. Eventually, this white dwarf will continue to cool until it becomes a black dwarf. This process is incredibly slow, and the white dwarf will gradually fade away, leaving nothing but darkness in its wake. The death of a star like our Sun is calm and quiet, a gradual fade into the night. But for massive stars, those much larger than our Sun, the story is far more dramatic. These stars burn through their fuel quickly, racing toward a violent end. Once they have exhausted their hydrogen, they begin fusing heavier elements, such as helium, carbon, and even iron. But here, a problem arises. Iron is special. Unlike the lighter elements, it cannot release energy through fusion, and energy is what keeps a star stable. Without the energy from fusion to push outward, the core of the star begins to collapse under its own immense gravity. This collapse happens in an instant, and when it does, something incredible occurs. The collapse of the core triggers a supernova, a truly enormous explosion. This explosion is so powerful it sends shockwaves throughout the entire star, blasting its outer layers into space. The result is one of the most brilliant and energetic events in the entire universe. A supernova lights up the sky, releasing more energy in a single moment than our Sun will in its entire lifetime. These explosions are not just spectacular displays of light, they also create the building blocks for new stars and planets. The heavy elements forged in the heart of these dying stars are scattered across space, enriching the cosmos and setting the stage for the formation of future generations of stars and planets. Supernovae are much more than just breathtaking explosions in the night sky. In fact, they play a crucial role in the universe, acting as the factories where the most essential building blocks of the cosmos are made. During a supernova, stars explode with incredible force, creating elements that are heavier than iron, such as gold, silver, and uranium. These elements are scattered far and wide into the surrounding space, seeding new stars and planets with the very ingredients needed for life. But the story doesn't end with the explosion itself. What happens afterward is just as extraordinary. What remains after a supernova depends on the mass of the star's core. If the core is between 1.4 and 3 times the mass of our Sun, it doesn't simply vanish, it collapses into a neutron star. Neutron stars are incredibly dense objects. To put this in perspective, just a teaspoon of neutron star material would weigh more than 1 billion tons on Earth. These stars are extreme in every sense of the word. They rotate at mind-boggling speeds, and some of them become pulsars, emitting powerful beams of radiation into space like cosmic flashlights. However, if the star's core is even more massive, it collapses even further, creating one of the most enigmatic and terrifying objects in the universe, a black hole. Here, the force of gravity is so intense that not even light can escape its pull. The matter from the star is crushed into an infinitely small point known as a singularity. A black hole is an area where the laws of physics as we know them break down. It's the end of one star's life, but the beginning of one of the most mysterious and extreme phenomena in the universe. The death of a massive star leads to the birth of objects that challenge our understanding of the cosmos. Neutron stars and black holes are just some of these remarkable remnants. These objects serve as a reminder of the immense power and chaos of the universe. But while stars have individual life cycles, they don't live alone. They are part of something much larger: galaxies. Galaxies are vast cosmic cities made up of stars, gas, dust, and dark matter, all held together by gravity. The Milky Way, the galaxy that includes our solar system, is just one of trillions in the universe. But how did these enormous collections of stars come to exist in the first place? The formation of galaxies began long ago, in the early universe. The first stars didn't just appear in empty space, they were born within enormous clouds of gas. These clouds were massive and could contain huge amounts of gas and dust. Over time, these clouds were pulled together by the force of gravity. As they collapsed, they began to spin, forming flat, rotating disks of gas and newly forming stars. This was the birth of the first galaxies, the foundations of the vast and complex structures we see in the universe today. As galaxies formed, they didn't just sit in place, they interacted with each other. They collided, merged, and evolved over billions of years, shaping the universe into the cosmic web of stars, planets, and galaxies we observe. By studying how galaxies form and interact, we can begin to understand the bigger picture of how the universe works and how it has become the vast, ever-changing space we see around us. Galaxies are not just random collections of matter. They follow a fascinating and intricate process of formation, guided by forces we can't always see, but which are incredibly powerful. One of the most crucial but invisible players in the formation of galaxies is dark matter. Dark matter is a mysterious substance that we cannot see because it doesn't give off any light. Unlike stars or planets, dark matter doesn't shine, making it invisible to our eyes and even our most powerful telescopes. But just because we can't see it doesn't mean it isn't important. In fact, dark matter is incredibly influential, especially when it comes to galaxies. Even though it's invisible, dark matter has a massive gravitational pull that shapes the universe. It makes up most of the mass in galaxies, and its gravity acts like an invisible scaffold that helps pull everything together. Without dark matter, galaxies wouldn't have enough gravity to stay intact. You could think of dark matter as the invisible glue that holds galaxies and the whole structure of the universe together over billions of years. So, how does this all work? In the early stages of the universe, gas clouds started to form. These clouds of gas were pulled together by gravity, eventually creating the first proto-galaxies, which were the early building blocks of the galaxies we see today. Over time, these proto-galaxies evolved into full-fledged galaxies, with some forming into spiral shapes, like our very own Milky Way, and others taking on more spherical shapes like elliptical galaxies. But galaxies don't form in isolation. They interact with each other in dramatic ways. They can collide, merge, and influence one another, affecting their shape and evolution. These interactions can be violent, as galaxies crash into each other, causing the gas within them to collide as well. This often sparks bursts of new star formation, as the energy from these collisions forces gas to condense and form new stars. Some of the most breathtaking and dynamic galaxies we see today, known as starburst galaxies, are the result of these energetic collisions. Our Milky Way galaxy is actually on a collision course with the Andromeda galaxy, and in about 4 billion years, the two galaxies will crash into each other. When this happens, they will merge into one much larger galaxy, forever changing the night sky. It's hard to imagine what this event will look like, but it will be a spectacular, unforgettable transformation of our universe. Even as galaxies grow, evolve, and collide, they are all connected by a vast, invisible structure known as the cosmic web. This is an enormous network of galaxies, gas, and dark matter that stretches across the entire universe. It's like a giant cosmic tapestry, where galaxies are the threads that weave the universe together. The cosmic web is made up of massive filaments of dark matter and gas, linking galaxies and creating a structure that shapes the way everything in the universe is arranged. Galaxies don't exist alone, they are part of this much larger system. The way galaxies form, evolve, and interact is one of the most important processes in the universe. It defines the large-scale structure of the cosmos, shaping everything from the smallest stars to the largest galaxy clusters. Within these galaxies, stars are constantly being born, living, and dying, continuing the endless cycle of creation and destruction that defines the universe. From the collapse of gas clouds under gravity to the explosive birth of new stars, from the death of massive stars in supernova to the awe-inspiring formation of entire galaxies, the universe is in constant motion. Stars are born in clouds of gas, live out their lives in an array of shapes and sizes, and eventually die, often in dramatic explosions. These processes are essential to the ongoing evolution of the universe, and they are all connected by the invisible threads of dark matter. The universe is a dynamic, ever-changing system where galaxies collide and merge, stars are born and die, and dark matter quietly holds everything together. This cosmic dance has been unfolding for billions of years, and it's still happening today, shaping the future of everything in the cosmos. In astronomy, dark matter is a mysterious and invisible type of matter that we can't see because it doesn't interact with light or any other kind of radiation. We know it exists because of the strange effects it has on gravity, which can't be fully explained by the laws of physics unless there's more matter around than we can actually see. These mysterious effects show up when we study things like how galaxies form and change over time, how light bends around massive objects called gravitational lensing, and even the way galaxies move within clusters. We also notice its influence in the structure of the universe and the leftover radiation from the Big Bang, the cosmic microwave background. In the most widely accepted model of the universe, known as the Lambda CDM model, the universe's total mass and energy is made up of 5% normal matter, the kind we see around us, 26.8% dark matter, and 68.2% dark energy. That means dark matter makes up about 85% of the total mass, while dark matter and dark energy together account for 95% of the universe's total energy. We don't know exactly what dark matter is, but it doesn't seem to interact with regular matter or light, except through gravity, making it almost impossible to detect with our current technology. The leading theory is that dark matter might be made up of tiny, unknown particles, such as weakly interacting massive particles, WIMPs, or axions. Another possibility is that dark matter could be made of ancient black holes from the early universe. Dark matter can be classified in different ways based on how fast its particles move, cold, warm, or hot. Most scientists think dark matter is cold, meaning its particles move slowly, allowing them to gather together and form structures over time. While most astrophysicists believe dark matter exists, some still question the idea. A small group of scientists, puzzled by certain observations that regular dark matter doesn't fully explain, suggest that perhaps the laws of gravity need to be adjusted. They've proposed alternative theories like modified Newtonian dynamics or new types of gravity, but none of these theories can perfectly explain all the evidence we've gathered so far. This suggests that, even if gravity needs some changes, dark matter still seems to be a necessary part of the puzzle. The idea of dark matter has a long and fascinating history, filled with curious discoveries and theories that laid the foundation for our current understanding of the universe. The story begins with the work of some of the brightest minds in science, starting in the late 19th century. In 1884, William Thomson, better known as Lord Kelvin, made some intriguing observations. He discussed the possible number of stars surrounding our sun in a book based on a lecture series he gave in Baltimore. Kelvin was trying to estimate the density of stars near the sun. He did this by studying the movement of stars around our solar system. Using this data, he wondered what would happen if there were 1 billion stars within a distance of 1 kiloparsec from the sun. At this distance, the stars would appear to move in ways that were hard to explain, and this idea set the stage for further thinking about invisible matter in space. Lord Kelvin also estimated the sun's age to be between 20 and 100 million years, which was later proven to be incorrect. But his curiosity about the stars and their movement contributed to early thoughts on dark matter. A couple of decades later, in 1906, the French mathematician and physicist Henri Poincaré introduced the term dark matter or matière obscure while discussing Lord Kelvin's work. Poincaré suggested that there might be hidden mass in the universe, but he also thought that this hidden matter would be less than the visible matter we can see. Although his ideas were far from correct, Poincaré's mention of dark matter brought the concept into the scientific conversation. In the 1920s, dark matter continued to intrigue astronomers. In 1922, Dutch astronomer Jacobus Kapteyn became one of the first to use the velocities of stars to suggest the existence of dark matter. He noticed that the way stars move in space could be influenced by unseen forces, hinting at the presence of invisible matter. Then, in 1930, Swedish astronomer Knut Lundmark further expanded on the idea, recognizing that the universe must have much more mass than we could observe with our telescopes. This realization was groundbreaking because it showed that the visible universe might not be the full picture. In 1932, another Dutch scientist, Jan Oort, joined the conversation by suggesting that dark matter might exist in the galactic neighborhood. Oort studied the movements of stars near our galaxy and concluded that there must be more mass in our galaxy than was visible. However, he later realized that his measurements weren't entirely accurate, and further research would be needed to understand the true nature of this unseen mass. Then, in 1933, Swiss astrophysicist Fritz Zwicky made a significant breakthrough while studying galaxy clusters at the California Institute of Technology. Zwicky was investigating the Coma cluster, a large group of galaxies, and noticed something strange. The galaxies in the cluster were moving far faster than expected based on the visible mass. This led him to suggest the presence of a huge amount of invisible mass, which he called dunkle materie, dark matter. Zwicky estimated that the Coma cluster had around 400 times more mass than could be seen through telescopes based on how the galaxies were moving. He believed that this unseen mass was responsible for the gravitational force that kept the galaxies in the cluster together. Although Zwicky's estimates were off by a large margin, mainly due to outdated values, he was one of the first to correctly identify that the universe must contain unseen mass that exerts gravitational pull. Zwicky, however, had a different view of dark matter than we have today. He believed that dark matter was simply ordinary matter that didn't emit light rather than something entirely different, like the mysterious dark matter we think of today. Nonetheless, his work was a major stepping stone toward the discovery of dark matter. As time went on, more evidence pointing to the existence of dark matter began to appear. One of the key pieces of this evidence came from studying galaxy rotation curves. In 1939, H.W. Babcock studied the rotation of the Andromeda galaxy, the nearest spiral galaxy to us. He found that the stars on the outer edges of the galaxy were moving much faster than expected. This suggested that there was much more mass in the galaxy than could be seen by just looking at its visible stars. Initially, Babcock suggested that the unusual rotation could be due to light being absorbed within the galaxy, or that the dynamics of the galaxy were different in its outer parts. But his observations were an early hint that something invisible was influencing the galaxy's rotation. The following year, in 1940, Jan Oort made another important discovery. He studied a galaxy called NGC 3115 and found a large invisible halo of mass surrounding it. This was another indication that galaxies might contain hidden matter beyond what we could observe with our current technology. The idea of dark matter really started to take hold in the 1970s. Different scientific discoveries were brought together to suggest that galaxies might be surrounded by massive invisible halos of matter. In 1974, two separate research groups, one from Princeton, New Jersey, led by Jeremiah Ostreicher, Jim Peebles, and Amos Yahill, and another from Tartu, Estonia, led by Jan Einasto, Ain Saar, and Ants Karsik, came to the same conclusion independently, strengthening the theory. One key observation that pointed to the existence of these invisible galactic halos was the way galaxies rotate. Both optical and radio astronomy played a major role in these findings. Vera Rubin and Kent Ford, using a new spectrograph, made more accurate measurements of the velocity of edge-on spiral galaxies, revealing unexpected results in the rotation curves. At the same time, radio astronomers used advanced radio telescopes to study the 21 centimeters line of atomic hydrogen in nearby galaxies. Unlike starlight, which can only be seen from the central parts of galaxies, hydrogen gas extends much farther out. This allowed astronomers to observe rotation patterns at much greater distances, giving them a better picture of the total mass in a galaxy. Early studies of the Andromeda Galaxy, using massive telescopes like the 300-foot Green Bank telescope and the 250-foot Jodrell Bank dish, showed that the hydrogen rotation curve didn't behave as expected based on Kepler's laws, which describe how objects should move around a center of gravity. As technology improved, more sensitive equipment allowed for even further measurements. In 1975, Roberts and Whitehurst pushed the boundaries, measuring the rotational velocity of Andromeda all the way out to 30 kpc. Their findings showed that the galaxy's rotation curve remained flat even at great distances. This was important because it suggested there was much more mass out there, beyond what we could see with regular telescopes. These findings, shown in their charts, combined optical data with the new hydrogen data, clearly illustrating the surprising flatness of the outer galaxy rotation curve. The solid curve in the graph represented the optical data from stars, while the other curve showed the cumulative mass, which still kept increasing even in the galaxy's outermost regions. At the same time, scientists were developing even more advanced techniques to study galaxies. Using interferometric arrays, multiple radio telescopes working together, researchers like Rogstad and Shostak in 1972 mapped the hydrogen rotation curves of 5 spiral galaxies. They discovered that all of these galaxies had flat rotation curves as well, suggesting that the mass in the outer parts of the galaxies was much higher than what could be accounted for by visible stars and light. By the late 1970s, it was widely accepted that dark matter halos likely existed around galaxies, and this became one of the biggest mysteries in astronomy. In the 1980s and 1990s, many observations began to suggest that dark matter was real. One important study, conducted by Persic, Salucci, and Stell in 1996, looked closely at 967 spiral galaxies and found strong evidence of dark matter's existence. Other supporting evidence included strange behaviors like gravitational lensing, where galaxy clusters bend light from objects behind them, the distribution of hot gas in galaxies and clusters, and the way tiny temperature differences, called anisotropies, show up in the cosmic microwave background, which is the afterglow of the Big Bang. Today, most scientists agree that dark matter is made up of particles that we haven't discovered yet, and these particles are unlike anything we know. The search to find this mysterious particle has become one of the biggest quests in particle physics, with many researchers using different methods and experiments to try and uncover the truth. In basic terms, when scientists talk about matter in the universe, they are referring to anything that contributes to the overall energy, and its density changes in a particular way as the universe expands. Specifically, it decreases as the cube of the expansion, meaning the further the universe stretches, the thinner the matter becomes. This is different from radiation, which decreases even faster. Its energy gets weaker as the universe grows, following the inverse fourth power of the expansion. On the other hand, the cosmological constant behaves differently. It stays the same no matter how much the universe stretches, meaning its energy density remains constant. This difference in how matter, radiation, and the cosmological constant behave is due to a phenomenon called radiation redshift. To picture this, imagine the universe expanding. If the observable universe's size doubles, the scale factor of expansion also doubles. As a result, the energy of things like the cosmic microwave background radiation, the afterglow from the Big Bang, gets weaker, because each photon, light particle, has to stretch out over a larger area, reducing its energy. The same happens to ultra-relativistic particles such as early neutrinos. These lose energy in a similar way. However, the cosmological constant, being a property of space itself, doesn't change no matter how much the universe grows. As for dark matter, this term generally refers to parts of the universe that we cannot see, yet still have mass and obey similar laws to regular matter. However, in more specific terms, dark matter is often used to describe a particular kind of invisible matter that isn't made up of the usual particles we're familiar with, excluding something called missing baryons. Depending on the context, the meaning of dark matter can vary. The arms of spiral galaxies spin around their center, and as you move outward from the center, the visible mass density of the galaxy gets lower. If all the galaxy's mass were visible, it would behave like a simple system where most of the mass is concentrated at the center and objects orbiting it, much like how planets orbit the sun in our solar system. Based on Kepler's third law, we would expect the speeds of the objects to slow down the farther they are from the center, just like how the planets in our solar system move slower the further they are from the sun. But that's not what we see in galaxies. Instead, the rotation speeds of stars and gas in a galaxy remain constant or even speed up the farther out they are from the center. To explain this strange observation, it seems clear that the distribution of mass in spiral galaxies is different from the solar system. Specifically, there may be a large amount of invisible non-luminous matter, what we call dark matter, on the outskirts of the galaxy. In bound systems like galaxies, the stars are also governed by a rule called the virial theorem, which helps explain how mass is spread out in a system based on the speeds of the stars. When astronomers look at how fast stars are moving in systems like elliptical galaxies or dense star clusters, they can use this theorem to figure out how mass is distributed. However, in many cases, the measured speeds don't match what we'd expect based on the amount of visible mass in the system, even when we consider complex orbital patterns of the stars. Much like with the rotation curves of galaxies, the most logical explanation for this mismatch is that there's more invisible matter involved. Again, dark matter. Galaxy clusters are key to studying dark matter because we can measure their mass in 3 different ways. By looking at the range of speeds at which the galaxies in the cluster move, by studying the X-rays emitted by the hot gas inside the cluster. By analyzing these X-rays, we can determine the temperature and density of the gas, which lets us calculate the pressure. Using the balance between gravity and pressure, we can figure out the total mass of the cluster. Through gravitational lensing, where the mass of the cluster bends light from more distant objects. This lets us measure the cluster's mass without needing to directly observe the motion of the galaxies. All 3 of these methods point to the same conclusion. Dark matter makes up roughly 5 times the mass of all the visible matter in these clusters. One interesting result of Einstein's theory of general relativity is a phenomenon called gravitational lensing. This occurs when massive objects like galaxies or clusters of galaxies sit between a light source and the observer. These massive objects act like a lens, bending the light that passes through them, making the light from the source appear distorted. The important thing to know is that gravitational lensing only requires the presence of mass. It doesn't matter what the mass is made of. The more massive an object is, the stronger the bending of light will be. For example, imagine a cluster of galaxies lying between a very distant object like a quasar and us. In this case, the galaxies in the cluster will bend the light from the quasar, making it look different. When we talk about strong lensing, we're referring to the dramatic way the light from background galaxies can be bent into arc shapes as it passes through a massive object's gravitational field. This has been observed around many distant galaxy clusters, including one known as Abell 1689. By studying the shape of these arcs, scientists can figure out the mass of the galaxy cluster causing the bending. In the weak lensing scenario, the bending is much less noticeable, and galaxies don't turn into arcs. Instead, we see tiny distortions in the shapes of galaxies. By looking at these slight changes, scientists can learn about how dark matter is spread out in the universe. The patterns of mass and light from these observations match what we expect from studies of dark matter. Now, while both dark matter and ordinary matter are forms of matter, they behave very differently. Early in the universe, ordinary matter was charged and interacted strongly with light, which caused it to scatter. Dark matter, on the other hand, doesn't interact directly with light, but it still affects the universe in other ways. For example, it influences the cosmic microwave background, CMB, through its gravitational pull, especially on large scales. It also has an effect on the movement and density of ordinary matter. Because of these differences, ordinary matter and dark matter evolve in separate ways and leave distinct traces on the CMB. The CMB is very close to being a perfect blackbody, meaning it gives off a smooth, uniform temperature. However, there are tiny temperature differences, about 1 part in 100,000, that scientists can study. These small variations, called anisotropies, can be mapped out across the sky. When scientists break down this map into a graph called the angular power spectrum, they see a series of peaks that are evenly spaced but have different heights. The exact positions of these peaks depend on key factors in cosmology, and by comparing these positions to theoretical models, we can learn more about the universe's makeup. The first discovery of the CMB's anisotropies came in 1992 by the COBE satellite, but the resolution wasn't high enough to see the detailed peaks. In 2000, the Boomerang experiment, using a balloon to take measurements, found the first of these peaks. Later, the WMAP satellite and the Planck spacecraft measured these peaks much more precisely. Their findings supported the lambda CDM model of cosmology. Structure formation is the process that began shortly after the Big Bang, when small irregularities in the universe's density caused matter to collapse and form stars, galaxies, and clusters of galaxies. Before this period, the universe was uniform, with no significant differences in density, as described by the Friedmann solutions to general relativity. Over time, tiny fluctuations in density started to grow and clump together, turning the smooth, featureless universe into a more complex structure filled with stars and galaxies. In the early stages, radiation dominated the universe and had a major impact on matter. This radiation prevented ordinary matter's density fluctuations from growing and forming structure. If the universe only had ordinary matter, these fluctuations would not have had enough time to evolve into the galaxies and clusters we see today. The key to solving this problem lies in dark matter, which is unaffected by radiation. This allowed its density fluctuations to grow first, creating gravitational wells that later helped ordinary matter collapse into galaxies and other structures. The gravitational pull from dark matter acted like a magnet, pulling in ordinary matter and speeding up the formation of these large cosmic structures. A striking example of the impact of dark matter is the Bullet cluster, formed by the collision of two massive galaxy clusters. What makes the Bullet cluster particularly interesting is the difference between where the mass of the cluster is located according to gravitational lensing, the bending of light around massive objects, and where the visible matter is found. This discrepancy is hard to explain with alternative gravity theories, which expect gravitational lensing to happen only around visible matter. However, the standard theory of dark matter can easily explain this. The visible gas in the clusters, which interacts with light and other forms of radiation, was slowed down and cooled by electromagnetic forces during the collision. Dark matter, on the other hand, doesn't interact with light in the same way, so it passes through the collision unaffected, separating from the visible gas. This created two distinct lensing peaks, as observed. In addition to dark matter, astronomers use Type Ia supernovae as standard candles to measure distances across the universe. These supernovae have a known brightness, so by measuring how dim they appear, scientists can calculate how far away they are. This method has revealed that the universe is expanding faster and faster, a phenomenon usually attributed to dark energy. Baryon acoustic oscillations, BAO, refer to regular fluctuations in the density of ordinary matter, baryons in the universe, which occurred on large scales in the early universe. These oscillations were caused by sound waves traveling through the hot, dense fluid of photons and baryons before the universe cooled enough for atoms to form. The effects of these sound waves can still be seen in the cosmic microwave background, CMB radiation. As the universe expanded, dark matter and ordinary matter began to clump together, but the effect of the original oscillations weakened over time. However, we can still observe a slight preference for galaxies to be separated by about 147 million light-years, which is a subtle but measurable signature of these early oscillations. This pattern was predicted in the 1990s and confirmed in 2005 through large galaxy surveys like the Sloan Digital Sky Survey and the 2DF Galaxy Redshift Survey. By combining CMB observations with BAO measurements, scientists can get a precise estimate of important cosmic values, such as the rate of expansion of the universe and the amount of matter it contains. These results support the lambda CDM model, which is the current leading theory of cosmology. Large surveys of galaxy redshifts can help us create a three-dimensional map of how galaxies are spread out in the universe. However, these maps are not perfect because the distances we estimate are based on the redshift we observe. The redshift we measure is affected by two things. The main factor is the universe's expansion, but there's also a smaller influence from the galaxy's own motion, known as its peculiar velocity. In general, superclusters, groups of many galaxies, are growing more slowly than the average expansion of the universe because their gravity is pulling things together. On the other hand, voids, vast empty spaces between galaxies, are expanding faster than the universe as a whole. This difference in expansion causes some interesting effects. For example, galaxies that are located in front of a supercluster are moving toward it faster than expected, so their redshift will be a little higher than we would normally calculate for their distance. Conversely, galaxies behind the supercluster appear to have a slightly lower redshift than expected. This difference causes superclusters to look flattened along the line of sight, while voids look stretched. However, this effect is hard to notice in a single structure, since we don't know its exact shape. Instead, scientists can observe this effect by averaging data from many structures. The phenomenon was first predicted by Nick Kaiser in 1987 and was later confirmed in 2001 by the 2DF Galaxy Redshift Survey, with results matching what we expect from the Lambda CDM model of the universe. In a related field of study, the Lyman alpha forest refers to the collection of absorption lines found in the spectra of distant galaxies and quasars. These lines are caused by neutral hydrogen absorbing light at a specific wavelength, called the Lyman alpha transition. Observations of the Lyman alpha forest help astronomers test and refine cosmological models, with results that align with findings from the WMAP data. Dark matter is often grouped into three types: cold, warm, and hot. These labels don't refer to temperature, but instead describe the speed at which the particles were moving in the early universe. In simple terms, they indicate how far the particles traveled due to random motions before the universe began expanding and slowed them down. This distance is known as the free streaming length, FSL. The classification of dark matter depends on how this FSL compares to the size of a protogalaxy, an early cosmic object that would eventually turn into a small galaxy. If the FSL is much smaller than the size of a protogalaxy, it's considered cold dark matter. If it's about the same size, it's warm dark matter, and if the FSL is much larger, it's hot dark matter. There are also theories that suggest a mix of these types, which were more popular in the mid-1990s, but became less favored after the discovery of dark energy. The key idea behind the free streaming length is that, after the Big Bang, the universe began with small fluctuations in density, which were caused by tiny quantum variations at the smallest scales. As these particles moved from denser areas to less dense ones, the rapid expansion of the universe put a limit on how far they could travel. Faster particles, like those in hot dark matter, could travel further before the universe expanded too much, while slower particles, such as those in cold dark matter, couldn't move as far. This means that the free streaming length sets a limit on the size of structures that could form in the early universe. Hot dark matter would lead to the formation of large structures like superclusters, which would eventually break apart into galaxies. In contrast, cold dark matter allows for smaller structures like galaxies to form first. Recent observations, particularly deep-field images of the universe, show that galaxies were the first to form, followed by clusters and superclusters as galaxies group together. This supports the idea that most dark matter is cold, not hot. This is also why neutrinos, which move almost at the speed of light and would be considered hot dark matter, cannot account for most dark matter. Dark matter refers to any type of matter that interacts with visible matter, like stars and planets, mostly through gravity. This means that dark matter might not be made of a completely new type of particle, but could, in theory, include ordinary matter like protons or neutrons. In fact, many objects familiar to astronomers, such as planets, brown dwarfs, red dwarfs, stars, white dwarfs, neutron stars, and black holes, fall into this category. For example, when a black hole pulls in matter, it doesn't differentiate between regular matter, like protons, and other kinds of matter. Once it's inside the event horizon, all matter is treated the same. These hard-to-detect objects are grouped together as machos, massive compact halo objects. Some scientists once thought that machos made up the majority of dark matter, but this idea has since been largely discounted. There is strong evidence suggesting that most of dark matter is not made up of ordinary visible matter. First, if there were enough regular matter like gas or dust scattered around, we would be able to see it when it's lit up by the light from stars. However, we don't see this kind of matter in the quantities we would expect. Next, the Big Bang theory helps us understand how the elements we observe today were created. According to this theory, if there were more normal matter called baryons in the early universe, we would have seen a higher abundance of elements like helium, lithium, and other heavier elements. Based on what we observe, we know that only about 4 to 5% of the universe's total mass consists of this regular matter. However, large-scale studies of galaxies and other cosmic structures show that the total amount of matter is about 30% of what is needed to keep the universe stable. Further investigations have shown that only a small portion of dark matter seems to be in the form of ordinary hidden objects, like small planets or black holes, called machos. Studies involving the bending of light by gravity, gravitational microlensing, suggest that these objects can't account for the majority of dark matter, as their masses fall within a range that excludes nearly all of the plausible candidates. Detailed studies of the cosmic microwave background, the faint radiation left over from the Big Bang, by missions like WMAP and Planck, provide strong evidence that about 5/6 of the matter in the universe doesn't interact much with light or regular matter, except through gravity. This suggests that dark matter is largely invisible and can only be detected through its gravitational influence. If regular matter, called baryonic matter, doesn't account for most of dark matter, then dark matter must be made of something else, specifically non-baryonic matter. There are two main possibilities for non-baryonic dark matter: new mysterious particles and ancient black holes from the early universe. Unlike baryonic matter, these non-baryonic particles don't help create the elements that formed during the Big Bang, a process known as Big Bang nucleosynthesis. Instead, we only notice them because of the gravitational effects they produce, such as how they bend light, called weak lensing. Some types of dark matter can even interact with each other, self-interacting dark matter, or with regular particles like WIMPs, weakly interacting massive particles. These interactions might produce detectable signs, such as gamma rays and neutrinos, which scientists could potentially observe, indirect detection. There are many different candidates for dark matter, each with strengths and weaknesses. WIMPs don't have a strict definition, but they are generally thought of as elementary particles that interact through gravity and possibly other weak forces, such as the weak nuclear force. Many theories suggest that WIMPs were created in the early universe in a similar way to regular particles. These particles would make up what's called cold dark matter. To explain how much dark matter we have today, the WIMP particles would need to be able to annihilate with each other in a specific way, which matches what would happen if they had masses around 100 giga-electron-volts and interacted through the electroweak force. This idea is often referred to as the WIMP miracle because it fits so well with predictions from supersymmetric theories, which extend the standard model of particle physics. A stable partner particle from supersymmetry has long been seen as a prime candidate for dark matter. Researchers are working hard to find WIMPs by looking for the products of their annihilations, such as gamma rays, neutrinos, and cosmic rays coming from nearby galaxies. They also use experiments designed to directly detect WIMPs in laboratories by measuring their interactions with atomic nuclei, or by trying to create WIMPs in particle colliders like the Large Hadron Collider, LHC. However, in the early 2010s, experiments didn't find strong evidence for supersymmetry, and the LHC results cast doubt on the simplest WIMP ideas. Axions, another candidate for dark matter, are theoretical particles that were first proposed in 1978 by Frank Wilczek and Steven Weinberg. These particles were originally suggested to solve a problem in the theory of quantum chromodynamics, QCD, which explains how quarks and gluons interact. Axions are incredibly light and weakly interact with other particles, making them a perfect candidate for dark matter. They could be produced in the early universe and would remain present today, their abundance depending on their mass. Axions are thought to be so light that they could help explain some of the small-scale issues in the lambda CDM model, the leading cosmological model. The axion theory has gained traction in recent years, especially after WIMPs were not detected. The axion's extremely low mass means that quantum effects could potentially explain the small-scale mysteries of dark matter. Primordial black holes, another intriguing idea, are thought to have formed in the very early universe, right after the Big Bang. During the period of rapid expansion known as inflation, incredibly dense regions of subatomic matter could have collapsed under their own gravity, creating black holes without the need for a star's death, as is the case with regular black holes. These black holes would predate the formation of the first stars and could have masses ranging from tiny, even as small as atoms, to incredibly large, far beyond typical stellar black holes. The concept of primordial black holes was first suggested in 1967 by Yakov Zeldovich and Igor Novikov, and later by Stephen Hawking in 1971. The idea quickly gained traction as a potential explanation for dark matter. One of the advantages of primordial black holes as dark matter candidates is that the theory behind black holes is already well established in physics, general relativity, and black holes themselves are already known to exist. However, creating primordial black holes might require complex conditions, such as exotic cosmic inflation or theories beyond the standard model of particle physics. In 2015, gravitational wave measurements from the detection of black hole mergers sparked renewed interest in primordial black holes as dark matter. Some black holes detected by these experiments had masses that seemed too large to be formed by the usual processes, like the collapse of a star. This suggested they could be primordial. However, a study that looked for signs of gravitational lensing from intermediate mass black holes, expected to be dark matter, found no evidence for them, although some researchers suggest this could be due to assumptions about the mass of these black holes. Further observations, like those made by the James Webb Space Telescope, may provide more clarity on this theory. Scientists once thought that incredibly small black holes, known as primordial black holes, might make up a significant portion of dark matter. However, the Voyager 1 spacecraft, which explored beyond the Sun's influence, measured the flow of positrons and electrons and found something surprising. The amount of particles detected was too low, and their energy levels were not what scientists expected. This led researchers to conclude that these tiny black holes are too rare to account for dark matter. Despite this, the idea of dense forms of dark matter continues to be researched, with new theories even suggesting ways to cool dark matter. As of 2018, the mystery remains unsolved. In 2019, further observations of the Andromeda galaxy showed no signs of microlensing effects, which would be expected if tiny black holes were present, adding more doubt to their existence. However, there's still a gap in our understanding. There is a range of mass smaller than what we can currently detect with optical microlensing, where primordial black holes could potentially make up all of the dark matter. This area remains open for exploration and continues to challenge our understanding of the universe. If dark matter is made of particles that barely interact with anything, an important question arises. Could these particles form objects like planets, stars, or black holes? Historically, the answer has been no, and there are two key reasons for this. It can't easily lose energy. Regular matter forms dense objects like stars and planets because it can lose energy in many ways. For example, when particles fall inward due to gravity, they can lose energy, which allows them to slow down and condense into more stable objects. Dark matter, however, doesn't seem to have the ability to lose energy because it doesn't interact with other matter strongly, except through gravity. Without ways to release energy, dark matter particles that start to get pulled inward would just heat up, speed up, and eventually escape, preventing the formation of compact objects. It doesn't interact in diverse ways. Regular matter interacts through multiple forces, such as gravity, electromagnetism, and the strong nuclear force, allowing it to form complex structures like atoms, stars, and galaxies. For instance, inside stars, particles interact through nuclear fusion, emitting light and neutrinos. In dark matter, we don't see evidence for such interactions beyond gravity, and possibly some weak interactions, but this is still speculation. Without these varied interactions, dark matter doesn't have the ability to form the kinds of structures that regular matter does. If dark matter is composed of subatomic particles, these particles pass through every square centimeter of Earth millions or even billions of times every second. Many experiments are trying to test this idea. While WIMPs, weakly interacting massive particles, have been the most commonly searched for candidates, Axions are also getting attention, especially with projects like the Axion Dark Matter Experiment, ADMX. Other possibilities include heavy particles from a hidden sector that only interact with regular matter through gravity. There are two main types of experiments investigating dark matter: direct detection experiments. These look for signs that dark matter particles are scattering off atomic nuclei in a detector. The goal is to measure tiny energy shifts, a few keVs, caused by these interactions. When dark matter hits an atom, the atom might release energy in the form of light or vibrations, which can be detected. To do this well, these experiments need to be as isolated as possible from background interference, which is why they are often conducted deep underground, where cosmic rays don't interfere. Notable underground labs include Starwell Mine, Sudan Mine, and the Gran Sasso National Laboratory. These experiments often use two technologies: cryogenic detectors that measure heat from particle collisions in materials like germanium, noble liquid detectors that detect light produced when a particle hits liquids like xenon or argon. Some prominent experiments in these areas include CDMs, CREST, xenon, and LUX. These detectors are particularly good at distinguishing dark matter from background particles, which mostly scatter off electrons, while dark matter particles scatter off atomic nuclei. Indirect detection experiments. These look for the after effects of dark matter particles annihilating or decaying. There's currently no confirmed detection of dark matter in direct detection experiments, but these efforts have helped narrow down the possible properties of dark matter particles. One interesting claim comes from the Dharma Nai and Dharma Libra collaborations, which have noticed a yearly fluctuation in their data, possibly due to the Earth's motion through the dark matter halo. However, other experiments, such as LUX and super CDMs, have not observed the same effect, creating a bit of a mystery. There are also special experiments with directional sensitivity, which track the motion of dark matter particles based on the solar system's movement around the galactic center. This technique tries to separate dark matter signals from background noise, which should be evenly distributed. These experiments, such as DMTPC and DRIFT, attempt to detect the direction in which dark matter is moving to help identify potential signals. Indirect detection experiments aim to find signs of dark matter by looking for the products that emerge when dark matter particles self-destruct or decay in space. In certain regions with high concentrations of dark matter, like the center of the Milky Way, two dark matter particles might collide and annihilate each other, releasing gamma rays or pairs of normal particles and their opposites, antiparticles. Alternatively, if a dark matter particle is unstable, it might break down into standard particles or others, which could be detected indirectly through an unexpected surge of gamma rays, antiprotons, or positrons coming from areas with a lot of dark matter, like the Milky Way's core or distant galaxies. One of the challenges of this kind of search is that other cosmic events could produce similar signals, so multiple signals from different sources are needed to confirm a dark matter discovery. Dark matter particles that pass through the Sun or Earth might interact with atoms and lose energy in the process. This could cause dark matter to accumulate at the centers of these celestial bodies, increasing the chances for collisions or annihilation. These events could send out a unique signal of high-energy neutrinos, which could serve as strong evidence of dark matter made of WIMPs, weakly interacting massive particles. Instruments like Amanda, IceCube, and Antares are actively searching for this signal. In addition, the detection of gravitational waves by LIGO in 2015 opened the door for observing dark matter in new ways, especially if it exists as primordial black holes. Several experiments have tried to detect dark matter emissions, such as those from annihilation or decay. For example, the Energetic Gamma Ray Experiment telescope spotted more gamma rays in 2008 than expected from the Milky Way, but scientists believed this was due to errors in estimating the telescope's sensitivity. The Fermi Gamma Ray Space Telescope is continuing this search, and in 2009, it observed a puzzling excess of gamma rays from the center of the Milky Way. This could be a sign of dark matter annihilation, or an unknown group of pulsars. In 2012, a deeper analysis of Fermi data suggested a 130 giga-electron-volts signal from the Milky Way's core, which was interpreted as a possible result of WIMP annihilation. At even higher energies, ground-based telescopes have set limits on dark matter annihilation in dwarf galaxies and galaxy clusters. The Pamela experiment, launched in 2006, detected an unusual amount of positrons, which might come from dark matter or pulsars, though no similar excess of antiprotons was found. Similarly, the Alpha Magnetic Spectrometer aboard the International Space Station observed high-energy cosmic rays in 2013, possibly linked to dark matter annihilation. Another approach to finding dark matter involves trying to create it in a laboratory. Experiments like those at the Large Hadron Collider, LHC, may detect dark matter particles formed during proton collisions. Since dark matter doesn't interact much with regular matter, it might be spotted indirectly by noticing large amounts of missing energy and momentum that escape detection, while other particles from the collision are measured. The LEP experiment, using a similar method but probing the interaction between dark matter and electrons, also provides constraints on dark matter. Any discovery of dark matter in such experiments must be verified by findings from indirect or direct detection methods to confirm that the new particle is truly dark matter. Since dark matter has yet to be identified, many alternative theories have emerged to explain the same cosmic phenomena. General relativity, the theory that supports much of the evidence for dark matter, is well tested on the scale of the solar system, but hasn't been fully proven on galactic or cosmic scales. Some scientists propose that modifying general relativity could eliminate the need for dark matter. Well-known alternatives include MOND, modified Newtonian dynamics, TVES, a relativistic version of MOND, FR gravity, negative mass, dark fluid, and entropic gravity, among others. A key challenge for these alternative theories is that the evidence for dark matter comes from many independent sources. While it might be possible to explain a single observation, explaining all the evidence without dark matter is very difficult. Still, some alternatives have had limited success, like the 2016 test of gravitational lensing in entropic gravity and a 2020 measurement supporting MOND. Despite these successes, most astrophysicists believe that while modifications to general relativity could explain some of the observations, the overall data suggests that dark matter must exist in some form. In the study of the universe, dark energy is a mysterious type of energy that influences the cosmos on the largest scales. Its main role is to drive the rapid expansion of the universe. If the current model of cosmology is correct, dark energy makes up 68% of the total energy in the universe today. In comparison, dark matter accounts for 26%, and regular matter only makes up 5%. Other forms of energy, like neutrinos and photons, are almost insignificant in terms of their contribution. Despite its low density, around 7 by 10⁻30 grams per cubic centimeter, which is much smaller than that of normal or dark matter, dark energy still rules the universe's mass-energy balance because it is spread evenly throughout space. Scientists first began to suspect dark energy existed after studying the light from distant supernovae. Type Ia supernovae are incredibly useful for measuring distances because they shine with a constant brightness. By comparing their light to the redshift, which tells us how fast the supernova is moving away, scientists discovered that the universe is expanding faster and faster, instead of slowing down as they had once thought. Before this discovery, the idea was that gravity from all the matter and energy in the universe would gradually slow the expansion. Since this surprising finding, multiple lines of evidence have reinforced the idea that dark energy is real. Even though dark energy has been detected, we still don't fully understand what it is. Several theories try to explain its nature. One is the idea of a cosmological constant, which suggests that dark energy is a steady, unchanging energy spread evenly through space. Another idea is scalar fields, which are energy sources that change over time and across space, like quintessence or moduli. While a cosmological constant would remain the same everywhere and at all times, scalar fields could vary. There are also other theories, such as interacting dark energy, which proposes that dark energy could be influenced by other forces, and cosmological coupling, which suggests dark energy might interact with gravity in ways we don't yet understand. The cosmological constant is a term that can be added to Einstein's equations in general relativity. When viewed as a source term in these equations, it can be thought of as the mass of empty space, also known as vacuum energy. This energy could either be positive or negative, depending on how it's conceptualized. Einstein first introduced the cosmological constant as a way to make his equations describe a static, unchanging universe. He imagined this constant would act as a force that balances out the pull of gravity, using a kind of dark energy to keep everything from collapsing. To represent this concept, he used the symbol capital lambda. Einstein described it as empty space, acting like negative mass, spread throughout the vastness of the universe, helping to prevent collapse. However, it was soon discovered that this solution wasn't stable. Even a tiny variation in the universe's size would cause it to either expand uncontrollably or contract endlessly. In Einstein's model, the universe wasn't truly in balance. If the universe expanded even a little, this would release more vacuum energy, causing the expansion to speed up. If the universe shrank, it would continue to collapse. Einstein also proposed that empty space could have its own energy, which would not get weaker as space itself expanded. As space grew, this energy would grow too, leading to an accelerated expansion of the universe. This sort of expansion is inevitable due to the uneven distribution of matter across the universe. In 1929, Edwin Hubble's observations revealed that the universe wasn't static at all, it was actually expanding. This discovery made Einstein call his own earlier belief in a static universe his greatest blunder. In 1980, Alan Guth and Alexei Starobinsky suggested a theory about the early universe called cosmic inflation. They proposed that a repulsive force, similar to dark energy, caused an explosive, rapid expansion just after the Big Bang. This rapid expansion, known as inflation, is a key feature of modern theories of the universe's origins. However, the energy required for this inflation was much higher than the dark energy we see today. The exact connection between dark energy and inflation remains a mystery, but after inflationary theories gained acceptance, the cosmological constant seemed less relevant. During the 1980s, most cosmologists focused on models of the universe made up mostly of cold, dark matter, CDM, and a small amount of regular matter. These models seemed to match observations of galaxy formation, but they didn't fully explain everything. For example, they suggested a lower value for the Hubble constant than what was actually observed. They also struggled to explain large-scale galaxy clusters. These issues became more pronounced after the 1992 discovery of the cosmic microwave background's irregularities by the COBE spacecraft. New models were proposed, including the Lambda CDM model, which incorporates the cosmological constant. In 1998, observations of distant supernovae confirmed that the universe's expansion was accelerating, providing the first strong evidence for dark energy. Soon after, additional observations supported the idea of dark energy. In 2000, the Boomerang and Maxima experiments found key data in the cosmic microwave background that showed the universe's total energy density was very close to the critical density. In 2001, the 2DF Galaxy Redshift survey showed that matter made up about 30% of this critical density. The difference was explained by the presence of dark energy. More precise measurements from the WMAP satellite, taken from 2003 to 2010, continued to confirm the Lambda CDM model, offering a clearer picture of the universe's makeup. The term dark energy was first used in 1998 by Michael S. Turner, echoing the earlier concept of dark matter introduced by Fritz Zwicky in the 1930s. To truly understand how the universe expands over time and space, we need to make very precise measurements of its expansion. In the field of general relativity, we figure out how the rate of expansion changes by looking at the universe's curvature and a key relationship known as the cosmological equation of state. This equation describes how temperature, pressure, and the combined densities of matter, energy, and vacuum energy are connected in any given region of space. One of the major goals in modern cosmology is measuring the equation of state for dark energy, which is one of the biggest challenges in the field today. When scientists add the cosmological constant to the standard model of cosmology, the FLRW metric, they arrive at the Lambda CDM model. This model is often called the standard model of cosmology because it aligns closely with what we observe in the universe. Since 2013, the Lambda CDM model has been validated by a range of increasingly accurate cosmological observations, including data from the Planck spacecraft and the Supernova Legacy Survey. Early results from the Supernova Legacy Survey show that dark energy's behavior on average closely matches the predictions of Einstein's cosmological constant, with a precision of about 10%. Recent findings from the Hubble Space Telescope's Higher Z team suggest that dark energy has been present for at least 9 billion years, even before the universe began accelerating. Despite these observations, the true nature of dark energy is still unclear and remains a topic of much speculation. Dark energy is believed to be very smooth and evenly distributed across space, with little density, and it doesn't seem to interact with any of the known forces except gravity. Its extremely low mass, about 10 to 27 kilograms per cubic meter, means it's unlikely to be detectable in lab experiments. Despite being so thin and light, dark energy makes up around 68% of the universe's total energy density. This is because it is thought to fill all of the empty space evenly, exerting a huge influence on the expansion of the universe. One leading theory links dark energy to vacuum energy. Vacuum energy refers to the particles and antiparticles that are constantly being created and annihilated in empty space, in line with Heisenberg's uncertainty principle. This constant fluctuation in energy is often cited as a key contributor to dark energy. According to Einstein's theory of relativity, this vacuum energy should have gravitational effects. That means it contributes to the cosmological constant, which in turn plays a role in accelerating the universe's expansion. However, there's a huge problem. The theoretical value for vacuum energy predicted by quantum field theory is much larger than the observed value, and scientists are still struggling to resolve this disagreement. Regardless of what dark energy really is, it must have a very strong negative pressure to explain the universe's accelerating expansion. In general relativity, pressure works like mass when it comes to its gravitational effect. Both pressure and mass are part of the stress-energy tensor, which is the key quantity that determines how matter influences gravity. When applied to the universe's expansion, this negative pressure creates an effect that causes the universe to expand faster. If the universe were shrinking, this tension would actually slow down its contraction. This acceleration is sometimes called gravitational repulsion because it seems to push the universe apart, counteracting gravitational attraction. In the way we currently understand the universe, there are three main parts that make up everything we know: matter, radiation, and dark energy. Matter is anything that has mass or substance, and it behaves in such a way that as the universe expands, its energy density decreases at a rate proportional to the cube of the expansion factor. To make it clearer, imagine a box with ordinary particles inside. If the box gets twice as big, the energy of those particles decreases by a factor of 8 because the particles are spread out over a larger space. This is because the size of the box is increasing in 3 dimensions, so the energy density becomes lower. Radiation, like light or heat, behaves a bit differently. Its energy density decreases even faster than matter as space expands. This happens because not only does the energy get spread out over more space, but the light or radiation also becomes stretched in wavelength as the universe grows. This stretching, known as redshift, causes radiation to lose energy even more quickly than matter does. Then there's dark energy. Unlike matter and radiation, dark energy doesn't depend on how much space there is. It's an inherent part of the fabric of space itself. No matter how much the universe expands, dark energy stays the same. Its energy density remains constant. Unlike matter, which gets spread out and thins as space grows, dark energy doesn't get weaker or diluted. It's a mysterious force that keeps the universe's expansion accelerating. The evidence for dark energy, although indirect, comes from several different sources that work together to give us a clearer picture. Distance and redshift measurements. By studying the relationship between the distance to objects and their redshift, how much their light is stretched as the universe expands, scientists have found that the universe has expanded more in its later stages than in its earlier ones. This suggests something has been driving this accelerated expansion, which could be dark energy. Theoretical need for extra energy. The universe's flatness, meaning it doesn't seem to curve in any detectable way, requires a type of energy that isn't regular matter or dark matter. This is thought to be dark energy, which helps explain why the universe looks as flat as it does. Cosmic density waves. By observing large-scale patterns of mass density in the universe, scientists have noticed clues that support the existence of dark energy. These patterns, such as the arrangement of galaxies, give further insight into the universe's expansion and its mysterious force. In 1998, a team of astronomers called the High-Z Supernova Search Team studied Type Ia supernovae, exploding stars, and found something surprising. The universe's expansion was speeding up, not slowing down. Another group, the Supernova Cosmology Project, made similar findings in 1999. For their work, the researchers were awarded the Nobel Prize in Physics in 2011. Since then, many different observations have supported these results. Data from the cosmic microwave background, radiation left over from the Big Bang, the bending of light from galaxies, called gravitational lensing, and the structure of the universe all line up with the idea of dark energy, as predicted by the Lambda CDM model, a model of cosmology. Some critics argue that only redshift and distance measurements provide strong evidence, but other findings like cosmic microwave background patterns also hint at distances larger than expected from a universe without dark energy. Supernovae are vital tools for studying cosmology because they act like standard candles. Their known brightness lets astronomers measure their distance, helping track the universe's expansion. By comparing how far away a supernova is and how much its light has shifted, redshift, scientists can gauge how fast the universe is expanding. Type Ia supernovae are especially useful because they have a consistent and predictable brightness, making them some of the most reliable markers in space. Recent data suggest that dark energy makes up about 71.3% of the universe, with dark matter and regular matter accounting for the rest. The theory that describes how galaxies, stars, and other structures form and grow also supports the idea that matter only makes up 30% of the universe's critical density, the amount needed to make the universe flat. In 2011, the Wiggle-Z Galaxy Survey, which studied over 200,000 galaxies, added more evidence to the dark energy theory. Using a clever method, they measured the distances to galaxies up to 2,000 million parsecs away. This helped confirm that the universe has been expanding faster as time goes on, offering further proof of cosmic acceleration. For the universe to be flat, as observed, there must be an additional form of energy, since the total amount of observable matter, baryonic and dark, only accounts for 30% of what's needed. The rest, around 70%, must be something like dark energy. Data from the Wilkinson Microwave Anisotropy Probe, WMAP, found that about 72.8% of the universe consists of dark energy, with the rest being dark matter and regular matter. More recent data from the Planck spacecraft revised this to 68.3% dark energy, 26.8% dark matter, and 4.9% regular matter. Dark energy also explains certain patterns observed in the cosmic microwave background. When photons, light particles, pass through areas of intense gravity, like galaxy clusters or voids, empty space between clusters, they lose energy, creating cold and hot spots in the background radiation. This effect, known as the integrated Sachs-Wolf (ISW) effect, is another key indicator of dark energy. A newer approach to measuring dark energy involves using the Hubble constant, which tracks the universe's expansion over time by studying galaxies that have passively evolved. These galaxies act as cosmic clocks, and by measuring their age and redshift, scientists can directly estimate the universe's expansion rate at different points in its history. Dark energy remains one of the biggest mysteries in modern physics. Scientists believe it is a force that drives the universe's expansion, but they don't know exactly what it is or how it works. Because of this, researchers are tackling the problem from multiple directions. Some are re-examining Einstein's theory of gravity, some are trying to figure out the exact properties of dark energy, and others are looking for alternative explanations based on observations of the universe. One of the most straightforward ideas about dark energy is that it is a fundamental property of space itself. In this view, empty space isn't truly empty. It contains energy, often called vacuum energy. This concept is known as the cosmological constant, represented by the Greek letter lambda. It is the foundation of the widely accepted Lambda CDM model of the universe. Since energy and mass are linked by Einstein's equation, This vacuum energy should have a gravitational effect, influencing how the universe expands. However, there's a huge issue. Quantum physics predicts that the amount of vacuum energy should be vastly greater, about 120 orders of magnitude too large. If this prediction were correct, the universe would have expanded so violently that galaxies, stars, and planets could never have formed. For the universe to exist as we see it today, something must be cancelling out most of this energy, but not completely. Scientists don't yet understand why this happens. Some physicists believe that dark energy might not be a constant force at all, but rather a changing, evolving energy field. This idea is called quintessence. Unlike the cosmological constant, which remains the same everywhere, quintessence can vary across space and time. It behaves like a field that fills the universe, influencing its expansion in a more dynamic way. For quintessence to work, the energy field must be extremely light so that it doesn't clump together like ordinary matter. Some versions of this theory predict that the universe's expansion should be slightly slower than what the cosmological constant model suggests. However, no solid evidence has been found to confirm or disprove quintessence yet. Another major puzzle is why dark energy became dominant at this particular time in cosmic history. If the expansion of the universe had accelerated too early, galaxies might never have formed, and life as we know it wouldn't exist. Some scientists argue that this is just a coincidence, while others believe it might support the anthropic principle, the idea that the universe must be the way it is because we are here to observe it. However, some quintessence models include a tracker mechanism that naturally explains this timing by linking dark energy to the density of radiation in the early universe. Some extreme versions of quintessence predict even more bizarre effects. One type, called phantom energy, suggests that dark energy could actually increase over time. If this is true, the universe wouldn't just expand, it would eventually tear itself apart in a scenario called the Big Rip. In this terrifying possibility, galaxies, stars, planets, and even atoms would be shredded as the force of expansion grows uncontrollably. Another variation, called K-essence, involves unusual forms of energy that behave differently from anything we've seen before. Some versions of K-essence allow for negative kinetic energy, which could have unpredictable effects on cosmic evolution. In recent years, scientists have found inconsistencies in measurements of the universe's expansion rate, known as the Hubble tension. Some researchers believe this discrepancy could mean that only certain types of quintessence models, with additional interactions, are possible. Dark energy is one of the biggest mysteries in modern physics, but our understanding of it is deeply tied to Einstein's theory of general relativity. Some scientists believe that if general relativity were modified in certain ways, we might not need the idea of dark energy at all. There are many alternative theories trying to explain the universe's accelerating expansion without dark energy, but so far, none have been fully proven. In fact, a key discovery, the measurement of gravitational waves in the event GW170817, has already ruled out many of these modified gravity theories. According to astrophysicist Ethan Siegel, while alternative explanations often make headlines, the vast majority of experts in the field firmly believe that dark energy is real. Competing ideas just don't match observational data as accurately as the standard dark energy model does. Scientists estimate that the universe's expansion started speeding up around 5 billion years ago. Before that, gravity, mainly from dark matter and regular matter, was slowing the expansion down. However, as the universe grew larger, dark matter spread out and became less influential, while dark energy stayed nearly constant. Eventually, dark energy took over, causing expansion to accelerate. For every time the universe doubles in size, the amount of dark matter per unit of space is cut in half, but dark energy remains almost unchanged. Looking ahead, the fate of the universe depends on the nature of dark energy. If it remains constant, as in the cosmological constant model, the universe will keep expanding forever. Galaxies outside our local group will move away from us faster and faster, eventually surpassing the speed of light, not in violation of relativity, but because space itself is stretching. Some galaxies that are already moving away faster than light may still send signals that reach us, but over time, the universe's expansion will create a point of no return. Beyond this cosmological event horizon, any light or signals emitted will never reach us, no matter how long we wait. Currently, this event horizon is estimated to be about 16 billion light-years away. That means if an event occurs within that distance, its light may still reach us in the far future. But anything happening beyond that distance will forever be beyond our observational reach. As galaxies near this horizon, the light they emit will get stretched to longer and longer wavelengths, eventually becoming invisible. From our perspective, those galaxies will simply fade away, leaving only our local group visible in an otherwise empty universe. Over trillions of years, our local group will remain intact, but it will eventually reach a state of heat death, where all energy is evenly spread out and no useful work can be done, similar to the fate once predicted for a matter-dominated universe before the discovery of cosmic acceleration. There are, however, more dramatic possibilities for the universe's future. One idea, known as phantom energy, suggests that dark energy could keep growing stronger until it overcomes every force in the universe. In this scenario, called the Big Rip, dark energy would eventually tear apart galaxies, stars, planets, and even atoms themselves. Another theory suggests that dark energy could change over time, possibly reversing its effects. This could lead to a big crunch, where the universe stops expanding and collapses back into a singularity. There's even a possibility that dark energy follows a cycle, causing the universe to expand, collapse, and then start over in a repeating cycle of big bangs and big crunches. While none of these more extreme ideas have been confirmed by observations, they remain intriguing possibilities. As research continues, the true nature of dark energy and the ultimate fate of the universe remain some of the greatest unsolved mysteries in cosmology. The timeline of the universe explains its history and future according to the theory of the Big Bang. The very first moments after the Big Bang, known as the Planck epoch, occurred in the first trillionth of a second, a picosecond. During this time, the usual laws of physics might not have applied. This period also saw the gradual appearance of the four basic forces we know today: gravity first, followed by electromagnetic forces, weak forces, and strong forces. The universe expanded rapidly in a process called cosmic inflation. Tiny fluctuations or ripples in the universe during this early time are believed to have played a key role in forming the large structures we see today, such as galaxies. While we understand some of the early universe's stages, we still don't have the tools to directly test them in particle physics experiments. However, by applying known physical laws to extremely high temperatures, we can still make educated guesses about what happened. For about 380,000 years after the Big Bang, the universe underwent dramatic changes. In the beginning, a mix of subatomic particles formed in stages. There was nearly an equal amount of matter and antimatter, but most of it destroyed itself in an explosion of energy, leaving a tiny amount of matter behind, which became the building blocks of everything we know. Around 1 second after the Big Bang, neutrinos, tiny particles that barely interact with anything, split off from other particles, creating what we now call the cosmic neutrino background. If primordial black holes existed, they would have formed around this time as well. Around 2 minutes later, protons and neutrons came together to form more complex subatomic particles. By the time 2 minutes passed, conditions were right for nuclear fusion, allowing the first elements to form. About 25% of the protons and all the neutrons fused into heavier elements, starting with deuterium, which quickly became helium-4. By 20 minutes after the Big Bang, the universe was no longer hot enough for nuclear fusion to continue, but still too hot for atoms to form or light to travel freely. At this point, the universe became a dense, opaque plasma. Around 18,000 years after the Big Bang, electrons began combining with helium nuclei, marking the start of the recombination epoch. By 47,000 years, as the universe cooled, matter began to dominate over radiation. By 100,000 years, after the neutral helium atoms formed, helium hydride was the first molecule to appear. Later on, hydrogen and helium hydride combined to form molecular hydrogen, which would become the fuel for the first stars. Around 370,000 years after the Big Bang, neutral hydrogen atoms fully formed during what is called recombination, which made it possible for photons, light, to travel freely. These photons were no longer scattered by free electrons and instead moved through the universe unimpeded. These ancient photons are still detectable today as the cosmic microwave background, CMB, the oldest light we can observe. From about 380,000 years to roughly 1 billion years after the Big Bang, matter began to clump together around pockets of dark matter. Slowly, clouds of hydrogen collapsed to form the first stars and galaxies. This period, known as the Cosmic Dark Ages, was a time when there were very few sources of light. Most of the photons that existed were the ones released during the decoupling process, which we still detect today as the cosmic microwave background, or 21 centimeters radio emissions from hydrogen atoms. Light was scarce, and the universe remained mostly dark until the first stars began to shine. Between 200 million to 500 million years after the Big Bang, the first stars and galaxies began to form, though scientists are still working to pinpoint the exact time. As the universe expanded, large structures slowly took shape, drawn together by dark matter filaments that acted like invisible webs, pulling matter into clumps. These early stars, which haven't been directly observed yet, were probably massive, some weighing 100 to 300 times more than our Sun, and made mostly of hydrogen and helium, with little to no metals. Because they were so big, they burned through their fuel quickly, living only a few million years before exploding in a powerful event called a pair instability supernova. Other theories suggest that some of these early stars could have been smaller, and perhaps a few of them are still shining today. These supernovae created the basic elements we see around us, like carbon and oxygen, and spread them throughout the universe, enriching it with the building blocks of life. Over time, galaxy clusters and superclusters began to form. Around 250 to 500 million years after the Big Bang, high-energy radiation from the first stars, small galaxies, and even quasars triggered a process known as reionization. This event slowly took place over a period that lasted until about 1 billion years after the Big Bang, although the exact timing is still being studied. It marked the end of the dark ages of the universe, a time when everything was still very dense and quiet. By 1 billion years, the universe was starting to look more like it does today, but it was a much hotter, more active place, full of smaller galaxies and more intense star formation. At this point, galaxies started to shift from being giant elliptical ones to smaller, unbarred spirals and irregular shapes. The earliest galaxies that scientists have observed date back to about 330 million years after the Big Bang, roughly 13.4 billion years ago. These galaxies were very young and contained few elements heavier than hydrogen, making them metal-poor. Spectroscopic evidence shows that they were surrounded by a cloud of neutral hydrogen, just as scientists expected. Studies also suggest that these galaxies formed quickly in an environment full of intense radiation. From around 1 billion years after the Big Bang, the universe began to look much like it does today, and it has continued in this state for the last 12.8 billion years. This period is expected to last for many billions of years to come. The Milky Way, for example, started forming its thin disk when the universe was about 5 billion years old, and our solar system came together about 9.2 billion years after the Big Bang. Life on Earth, however, began much later, about 10 billion years after the Big Bang. As the universe aged, matter began to thin out, which slowed its ability to pull the universe back together with gravity. At the same time, dark energy, an unseen force, started to take over, causing the expansion of the universe to accelerate. This shift occurred about 5 or 6 billion years ago, marking the beginning of the dark energy-dominated era, where the universe's expansion is speeding up instead of slowing down. While we have a good understanding of how the universe works today, we aren't sure what will happen in the far future, after around 100 billion years, or about 86 billion years from now. At some point in the distant future, the stelliferous era will come to an end. This will happen when stars stop being born, and as the universe continues to expand, we will only be able to observe galaxies that are close to us. The ultimate fate of the universe is still a mystery, with many possible scenarios to consider. As we learn more about the current state of the universe, we might be able to better understand what lies ahead. The expansion of the universe that we observe today led to the development of the Big Bang theory. This theory suggests that the universe started from a state of extremely high temperature and density. A refined version of this theory, known as the lambda CDM model, matches a wide range of astrophysical observations. However, when we trace this expansion backward in time to even higher temperatures and densities, we reach a point where current physical models fail to make accurate predictions or break down entirely. As we approach infinite temperature or a scale factor of 0, essentially the moment the universe began, our physical models no longer hold up. At this stage, theorizing about an initial gravitational singularity doesn't make sense because it falls outside the realm of our current understanding of physics. The standard model of cosmology tells us that the universe has been expanding since it was very hot. But as we try to trace this expansion backward, we reach a point known as the Planck length. Below this distance, the laws of physics we rely on don't apply anymore, and the energy in the particles becomes so extreme that quantum effects take over, overriding Einstein's gravity equations. The Planck time, which is incredibly brief, marks the beginning of the Big Bang according to cosmological models. After the Planck era, the universe could, in theory, be modeled by extensions of the standard model of particle physics, like grand unified theories, GUTs. However, no GUT has yet been able to match the results of modern observations. The time period between zeptosecond and rontosecond is known as the grand unification epoch, although this is still speculative. Before this grand unification epoch, the universe was so hot that its temperature exceeded quadrillion giga-electron volts. As the universe expanded and cooled, it may have passed through a phase transition, similar to how gas condenses into liquid or freezes into solid, which could explain the large amount of matter compared to antimatter we observe today. While the grand unification phase is still uncertain, transitions like the electroweak and quark-hadron phases are supported by theoretical models and have made successful predictions. The electroweak epoch, depending on the model, could have started before or after the inflationary epoch, or in some models, it could even overlap with it. In some views, it began after inflation ended, roughly rontoseconds, after the Big Bang. At this early stage in the universe's life, it is thought to have expanded by an enormous factor, at least sextillion times its original size. This is like taking something as small as a nanometer, about the width of a DNA molecule, and expanding it to a length of over 10.6 light-years, which is about 100 trillion kilometers, in just a tiny fraction of a second. This rapid expansion is known as cosmic inflation, and it marks a crucial period in the universe's development. The exact cause of inflation, the rapid expansion of the universe, is still not fully understood, even though many theories have been proposed. One popular idea suggests that inflation started when two fundamental forces, the strong and electroweak interactions, separated, ending a period called the Grand Unification Epoch. During this time, a special field known as the inflaton field was created. As this field spread across the universe and settled into its lowest energy state, it produced an immense repulsive force that caused the universe to expand at an incredibly fast rate. Inflation helps explain several strange features of the universe today that would otherwise be hard to understand. For example, it explains how the universe, which began as a uniform and evenly spread out space, now has galaxies and galaxy clusters. The small random fluctuations in the universe's early state, which were magnified during inflation, eventually formed the large-scale structures we see now. We don't know exactly when inflation ended, but it is believed to have stopped between 10 to 33 and 10 to 32 seconds after the Big Bang. The universe expanded so quickly that particles left over from the Grand Unification Epoch were spread out across vast distances. But then, at the end of inflation, the inflaton field released its energy, a process called reheating. This release of energy created a hot and dense mix of particles such as quarks, antiquarks, and gluons. Some theories suggest that this reheating phase marked the beginning of the electroweak epoch, while other models, like warm inflation, do not include a distinct reheating phase at all. After inflation, the universe continued to expand, but much more slowly. Around 4 billion years ago, the expansion began to speed up again, likely because dark energy started to take control of the universe's behavior. This accelerating expansion is still happening today. Following inflation, the universe was filled with a superheated plasma made of quarks and gluons, which was a leftover effect from reheating. After this stage, scientists have a much clearer understanding of what happened in the early universe, as the conditions of the quark epoch can now be recreated in particle physics experiments. As time passed, the particles that were created during inflation went through a process called thermalization, where they interacted with each other and reached a state of thermal equilibrium. Prior to a major change known as electroweak symmetry breaking, which occurred about 10 to 15 seconds after the Big Bang at temperatures around 1015 K, the electromagnetic and weak forces had not yet split apart. The particles involved hadn't yet gained mass through the Higgs mechanism. This phase came to an end when electroweak symmetry breaking happened, possibly as part of a phase transition. Some versions of the standard model of particle physics suggest that during this time, baryogenesis occurred, leading to a slight imbalance between matter and antimatter, though some theories propose this imbalance might have happened even earlier. The specifics of these events are still a mystery. As the universe's temperature continued to drop below 159.5 plus or minus 1.5 giga-electron volts, a crucial event known as electroweak symmetry breaking occurred. This event, which happened after the universe's initial expansion, was the second to last major change in the universe's structure, with the final one being chiral symmetry breaking in the quarks. This transformation had two important effects. First, through the Higgs mechanism, all the tiny particles in the universe began to gain mass. Before this, they were massless, but as the temperature dropped and energy levels decreased, these particles started interacting with the Higgs field and became massive. Second, the weak nuclear force and electromagnetic force began to behave differently. These forces, along with their associated particles, the W and Z bosons, which carry the weak force, and the photon, which carries the electromagnetic force, went through a dramatic change. Before the electroweak symmetry breaking, all of these forces and their particles were massless and could interact over long distances. But after the symmetry breaking, the W and Z bosons became heavy and could only act over distances smaller than an atom, while the photons stayed massless and continued to interact over vast distances. After this key event, the four fundamental forces, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, were established in the forms we recognize today. The basic particles also had their expected masses, but the temperature of the universe was still far too high for many particles to form in stable structures. So there were no protons or neutrons yet, and thus no atoms, atomic nuclei, or molecules. Any particles that managed to form briefly would break apart almost immediately due to the extreme energy levels. This period, known as the quark epoch, began roughly 10 to 12 seconds after the Big Bang. It was a time right after the electroweak symmetry breaking, when the universe's fundamental forces took their current forms, but the temperature remained too high for quarks to combine and form more complex particles. During this epoch, the universe was a seething mass of quarks, gluons, leptons, and their opposites, all existing in a hot, dense plasma. The energy from constant collisions between these particles was so high that quarks couldn't combine to form mesons or baryons. The quark epoch ended when the universe was about 10 to 5 seconds old. At this point, the temperature dropped enough for the energy from particle interactions to fall below the mass of the lightest particle formed from quarks, the pion. Baryons, such as protons and neutrons, are made up of 3 quarks, and it was expected that for every baryon created, an equal number of antibaryons would form as well. However, this didn't seem to happen. The universe ended up with far more baryons than antibaryons, and in fact very few antibaryons are observed in the universe today. Scientists are still unsure how this imbalance occurred. Any explanation must satisfy certain conditions related to baryogenesis, which took place after the universe's rapid inflation. While theories exist that might explain this imbalance, the asymmetries involved appear too small to fully account for the huge difference between baryons and antibaryons that we observe. The theory suggests that for every 6 protons, there was about 1 neutron, though this ratio eventually dropped to 1 neutron for every 7 protons due to neutron decay over time. This idea is supported by evidence that later on, neutrons and some protons fused together to form elements like hydrogen, a hydrogen isotope called deuterium, helium, and other elements, which we can still measure today. The 1:7 ratio of hadrons would lead to the same proportions of elements we see in the early and current universe. About 1 second after the Big Bang, neutrinos, tiny particles that hardly interact with matter, separated from the hot, dense matter and began traveling freely through space. These neutrinos, which are still around today, are similar to the cosmic microwave background, CMB radiation we observe today, which was emitted much later, around 370,000 years after the Big Bang. The neutrinos from that early time have extremely low energy. Detecting high-energy neutrinos is already difficult, so this background of cosmic neutrinos, CNB, may remain invisible for many years or perhaps forever. However, Big Bang cosmology predicts a lot about the CNB, and there's strong indirect evidence supporting its existence. This evidence comes from predictions about the amount of helium produced during Big Bang nucleosynthesis and from irregularities seen in the CMB. One of the predictions is that neutrinos would have left a faint mark on the CMB. We already know the CMB shows some uneven patterns. Some of these irregularities occur at regular intervals due to a process known as baryonic acoustic oscillations. According to the theory, the neutrinos that separated early on should have caused tiny shifts in the phases of these fluctuations. In 2015, scientists announced that they had detected these shifts in the CMB. The patterns they found matched the temperature of neutrinos predicted by the Big Bang theory. Furthermore, they detected exactly 3 types of neutrinos, matching the 3 flavors expected according to the standard model of particle physics. Primordial black holes are a speculative type of black hole proposed in 1966, which could have formed during the radiation-dominated era of the universe, if the universe had enough irregularities. Small variations in density might have caused certain regions to collapse under their own gravity, leading to the creation of black holes. Meanwhile, most hadrons, like protons and neutrons, and antihadrons, their opposites, would have destroyed each other, leaving behind leptons, such as electrons, muons, and neutrinos, and antileptons. In the early universe, leptons and antileptons appeared in pairs. About 10 seconds after the Big Bang, the temperature of the universe dropped enough that new lepton-antilepton pairs stopped forming. Most of the remaining leptons and antileptons annihilated each other, turning into high-energy photons. However, a small number of leptons survived, leaving a tiny residue behind that contributed to the mass of the universe. After most leptons and antileptons are wiped out at the end of the lepton epoch, the universe's energy mostly remains as photons. The rest is mainly in the form of neutrinos and other fast-moving particles. Because of this, photons become the dominant form of energy in the universe, and they control how the universe behaves. For the next 370,000 years, photons continue to interact regularly with charged particles like electrons, protons, and eventually atomic nuclei. Between 2 and 20 minutes after the Big Bang, nuclear fusion begins. During this time, a mix of neutrons and protons, about 1 part in 7, starts fusing into different elements like protons, deuterium, a proton fused with a neutron, and helium isotopes, such as helium-3 and helium-4, with trace amounts of lithium and beryllium. This process stops when the temperature drops below the level needed for fusion. The exact mix of elements created depends on factors like the reaction rates, temperature, and the density of the particles. Scientists can measure the reaction rates in labs, while temperature and density can be calculated using models of how the universe is expanding. About 25% of protons and all neutrons combine to form deuterium, a hydrogen isotope, and most of this deuterium quickly fuses into helium-4. Helium-4 has a stronger binding energy than nuclei with 5 to 8 particles, so very few of these heavier nuclei are made. Heavier elements that are created in stars don't form because they need 3 helium-4 nuclei to combine, but the universe's expansion is too fast for that to happen before the temperature cools down too much. Some tritium, another hydrogen isotope, and small amounts of beryllium-7 and beryllium-8 form but are unstable and decay quickly. A small amount of deuterium is left behind unfused. By studying old galaxies, scientists can estimate how much of each light element was created in the early universe, which strongly supports the Big Bang theory. For example, we see that about 1 neutron was created for every 7 protons, allowing for 25% of all particles to fuse into helium-4. This matches the amount we see today, which is much more than can be explained by stars alone. Deuterium, which fuses easily, also gives strong evidence for the Big Bang, as any alternative theory would need to explain why deuterium was formed and why some of it wasn't immediately fused into helium. Any alternative theory must also explain the exact proportions of the light elements and their isotopes, with some isotopes like lithium-7 showing small discrepancies from what theory predicts. For much of the universe's early history, its large-scale behavior was mostly determined by radiation, particles that move near the speed of light, such as photons and neutrinos. However, as the universe cools, around 47,000 years after the Big Bang, matter starts to take over. This happens because the density of matter starts to surpass both the density of radiation and the energy from empty space. Around this time, the densities of matter, in the form of atomic nuclei, and radiation, photons, become equal. This shift allows small structures to begin to form, as gravitational attraction can now overcome the pressure from radiation, leading to the growth of these structures instead of being wiped out by radiation. According to the lambda CDM model, by this point in the universe's history, about 84.5% of its matter consists of cold, dark matter, and the remaining 15.5% is made up of regular or ordinary matter. There's strong evidence supporting the existence of dark matter, which plays a dominant role in the universe's structure. However, scientists still don't fully understand what dark matter is, so the Big Bang theory doesn't yet explain how it formed. For billions of years ahead, dark matter will continue to influence how the universe's structure develops. In the early universe, dark matter started to clump together in enormous filaments because of gravity, pulling together much faster than ordinary matter. This is because dark matter doesn't interact with radiation like regular matter does. As it gathers, it enhances small irregularities in the universe's density that were left behind by cosmic inflation. Over time, regions that were slightly denser became even denser, while areas with fewer particles grew emptier. The presence of these dark matter concentrations helped regular matter come together more quickly than it would have on its own. One of the reasons dark matter clumps together so quickly is that it doesn't lose energy through radiation. For particles to form dense structures like stars or planets, they need to lose energy, but dark matter can't do this. Instead, it forms large, thin filaments and halos rather than compact objects. Regular matter, on the other hand, can lose energy by emitting radiation, which allows it to collapse into denser objects like stars or gas clouds. Around 370,000 years after the Big Bang, two major events occurred: recombination and photon decoupling. Recombination refers to the process where ionized particles, like electrons and protons, combine to form the first neutral atoms. Photon decoupling happens when the photons, which were previously trapped by interactions with these particles, were freed as the newly formed atoms reached stable energy states. Before recombination, the universe was extremely hot, and the matter was in the form of an ionized plasma. The photons kept interacting with the charged particles, preventing them from traveling far. Because of this, the universe was opaque, almost like a fog. There was light, but it wasn't possible to see through it with telescopes. As the universe cooled over time, starting around 18,000 years after the Big Bang, electrons began to combine with helium nuclei to form helium atoms. Neutral helium started to form at about 100,000 years, and hydrogen atoms followed around 260,000 years. This process is known as recombination, though the name is a bit misleading because it was the first time the electrons and nuclei combined. Around 100,000 years later, the universe had cooled enough for the first molecule to form, helium hydride. This was a breakthrough in the history of molecular chemistry. In April 2019, scientists confirmed that helium hydride had been observed in space, specifically in the planetary nebula NGC 7027. Later, this molecule would interact with atomic hydrogen, leading to the formation of molecular hydrogen, the key ingredient for star formation. When hydrogen atoms combine in a low-energy state, it's not very efficient. Instead, they usually come together while still holding on to their high-energy electrons. After the atoms combine, these electrons quickly release energy, transforming into lower energy states and emitting photons. This release of photons is called photon decoupling. Some of these photons are caught by other hydrogen atoms, while the rest remain free. By the time the process of recombination finishes, most of the protons in the universe have combined with electrons to form neutral hydrogen atoms. This shift from charged particles to neutral ones changes how far photons can travel before being captured. Essentially, after recombination, photons can travel freely without being blocked, making the universe transparent to light, radio waves, and other types of electromagnetic radiation for the first time. The photons released by these neutral hydrogen atoms had a temperature of around 4000 K, which would have looked like a soft white light with a pale yellow or orange tint to the human eye. Over billions of years, as the universe expanded, these photons stretched out, shifting from visible light to longer wavelength radio waves, which now correspond to microwave radiation with a temperature of about 2.7 K. This process, known as redshifting, occurs because the universe's expansion causes the wavelengths of photons to get longer and their frequencies to drop. These red-shifted photons can still be detected today as radio waves, forming what we call the cosmic microwave background. This radiation provides valuable clues about the early universe and its development. Around the same time as recombination, there were existing pressure waves in the electron-baryon plasma, which became locked into the distribution of matter as it condensed. These pressure waves, known as baryon acoustic oscillations, left behind a slight pattern in the large-scale structure of the universe. The cosmic microwave background captures a snapshot of the universe from the end of this period, including tiny fluctuations from the early moments of inflation. The spread of galaxies seen today reflects the scale and growth of the universe over time. After recombination and decoupling, the universe became transparent, but it was still too cool for stars or galaxies to form. Stars and galaxies only began to emerge when gravity caused dense regions of gas to collapse, a process that took hundreds of millions of years. This long wait is why stars didn't appear until much later after recombination. This time period, called the Dark Ages, started around 370,000 years after the Big Bang. During the Dark Ages, the universe cooled from about 4000 K to 60 K. Only two sources of photons existed during this time: the ones released during recombination, which we can still detect as the cosmic microwave background, CMB, and photons occasionally emitted by neutral hydrogen atoms, known as the 21 cm spin line. The 21 cm spin line is in the microwave frequency range. Within just 3 million years, the CMB photons had shifted out of visible light into the infrared spectrum. For a long time after that, there was no visible light in the universe, and aside from a few rare anomalies, it was truly dark until the first stars began to form. The first stars in the universe, called Population 3 stars, began to form just a few 100 million years after the Big Bang. These stars were the first to shine with visible light, marking the end of the universe's Dark Ages, a period when no light could be seen. Around 150 million years after the Big Bang, structures may have started to take shape, and by 180 to 700 million years later, early galaxies began to emerge. This gradual process continued, and it wasn't until about 1 billion years after the Big Bang that the Dark Ages fully ended, and the universe looked much more like it does today. Currently, the oldest stars and galaxies observed are from just after the beginning of a process called reionization, which occurred around 400 million years after the Big Bang. The Hubble Space Telescope in 2016 observed galaxies like GNZ 11, which existed about 400 million years after the Big Bang. The James Webb Space Telescope, launched in December 2021, is even more powerful and can detect galaxies that are 100 times fainter than those found by Hubble. Webb is expected to reveal objects from as far back as 180 million years after the Big Bang, which could be before the first galaxies even formed, and possibly from the time when the first stars were born. Scientists are also trying to detect a specific kind of faint radiation known as the 21 cm spinline radiation. This is an important tool for studying the early universe, even more powerful than the cosmic microwave background radiation that has already been used to learn about the universe's beginnings. Researchers are still working to determine the exact timeline of the first stars, galaxies, black holes, and quasars, as well as the precise start and end of the reionization period. New discoveries are constantly being made. For example, By 2019, scientists had confirmed galaxies like GNZ 11 that existed around 380 to 400 million years after the Big Bang. This suggests that gas clouds condensed and stars formed much faster than previously thought. Observations of the Lyman Alpha Forest, a pattern of light changes from ancient objects, help scientists narrow down the timing of reionization and its end. But there is still much to explore in these areas of research. In the Big Bang model, the formation of structures in the universe happens step by step, with smaller objects forming first before larger ones. The very first structures to appear were the first stars, called population 3 stars, tiny galaxies known as dwarf galaxies, and quasars. Quasars are extremely bright and active galaxies from the early universe, containing a supermassive black hole at their center, surrounded by a swirling disk of gas being pulled in. Before these structures began to form, scientists could study the universe using a simpler theory called linear cosmological perturbation theory. This idea suggested that the universe was mostly uniform, and any changes were just small variations. This made it easier to understand, as the universe seemed mostly smooth. But once the first stars and galaxies started forming, the situation became much more complex. Now, large clusters of particles started to interact in more complicated ways, so scientists needed more advanced techniques to study it, like simulations using billions of particles, known as N-body simulations. The Bolshoi cosmological simulation is one of the most accurate examples of this. The population 3 stars were not just important for lighting up the universe, they were also responsible for turning the light elements formed during the Big Bang, like hydrogen, helium, and a small amount of lithium, into heavier elements. These stars could be either massive or smaller, and they were made almost entirely of hydrogen and helium, with no heavier elements, which is why they're called non-metallic. The largest of these stars had short lives, burning through their hydrogen quickly and exploding as supernovae after just a few million years. These explosions spread heavier elements into space, which would eventually form future generations of stars and planets. This marked the beginning of what's called the stelliferous era, the era of star formation. So far, no population 3 stars have been directly observed. Our knowledge about them comes from computer models that try to simulate how these stars would have formed and evolved. However, scientists can still get clues about when star formation began by studying the cosmic microwave background radiation, which is leftover heat from the Big Bang. In 2016, observations made by the Planck Space Telescope suggested that the first stars started forming around 300 million years after the Big Bang. Quasars give us more hints about the early universe. The light coming from quasars contains elements like carbon, magnesium, iron, and oxygen. This means that by the time quasars appeared, there had already been a lot of star formation, including many generations of population 3 stars, which produced those heavier elements. As these first stars, dwarf galaxies, and quasars slowly formed, the powerful radiation they emitted started to ionize much of the universe. This process broke apart the neutral hydrogen atoms that filled space, turning them back into a plasma of free electrons and protons, a process that hadn't happened since the universe's early stages, known as recombination and decoupling. Reionization can be seen through the study of quasars, which are extremely bright, active galaxies and some of the most powerful objects in the universe. Quasars help scientists understand the history of the universe because they give us clues about how light interacts with different forms of hydrogen. In neutral hydrogen, electrons absorb ultraviolet light in specific patterns known as the Lyman series, which are tied to the energy levels of the electrons. But once hydrogen is ionized, it no longer has these energy levels. This means that light passing through ionized and neutral hydrogen will absorb light in different ways, showing different patterns of absorption. Ionized hydrogen in the space between galaxies, especially the electrons, can scatter light just as it did before reionization occurred, through a process known as Thomson's scattering. However, the universe had expanded and gas had clumped together into galaxies, so by the time reionization happened, the concentration of ionized hydrogen wasn't dense enough to block all light. As light travels vast distances, billions of light years, from distant objects to Earth, any absorption by neutral hydrogen is stretched out, making it more red, a shift in wavelength, by varying amounts. This stretching allows scientists to study the conditions of ionization during different times in the past. Reionization began as small bubbles of ionized hydrogen that grew larger over time, until eventually the entire space between galaxies was ionized. When this happened, neutral hydrogen became much rarer. This process wasn't influenced by light passing through galaxies or other dense areas, but was a result of the general state of the universe at that time. Reionization may have started around 250 million years after the Big Bang, a redshift of 16, and by around 500 million years, most of it was complete, a redshift of 9 or 10. The last traces of neutral hydrogen were fully ionized by about 1 billion years after the Big Bang, a redshift of 5 or 6, which was when scientists stopped seeing the absorption patterns that show the presence of neutral hydrogen. After this, the universe has remained mostly ionized, with only a few neutral hydrogen clouds remaining, which create features known as Lyman alpha forests in the light spectra we observe today. While we now know the rough time when reionization occurred, we still don't fully know what caused it. To ionize hydrogen, energy greater than 13.6 electron volts is needed, which comes from ultraviolet light with wavelengths shorter than 91.2 nanometers. This means the sources responsible for reionization must have produced lots of high-energy ultraviolet light. If the energy isn't constantly supplied, protons and electrons would recombine, which limits how long these sources could last and how many there were. Based on what we know, the most likely sources of energy for reionization are thought to be the first stars and galaxies, called population 3 stars, dwarf galaxies, and possibly quasars. Current estimates suggest that population 3 stars were the main contributors, with dwarf galaxies and quasars playing smaller roles. By the time reionization occurred, the universe had expanded and matter was spread out. While hydrogen was reionized, the plasma was much thinner and light was less likely to scatter. This made the universe mostly transparent during reionization. The process ended as the universe became nearly fully ionized, though pockets of neutral hydrogen still exist in some areas, creating the Lyman alpha forests we can observe today. In August 2023, the James Webb Space Telescope made an exciting discovery, capturing images of black holes and matter from the very early universe. These findings sparked a lot of discussions among scientists. Matter, under the pull of gravity, keeps clumping together, eventually forming galaxies. The stars created during this time, known as population 2 stars, formed first, while the newer population 1 stars came later. Gravity also causes galaxies to slowly move closer to one another, eventually forming groups, clusters, and even superclusters. The Hubble Ultra-Deep Field observations have shown smaller galaxies merging to create larger ones, about 800 million years after the Big Bang, which was roughly 13 billion years ago, though this age estimate is now believed to be a little too high. For billions of years, the universe has looked much like it does today, and will likely continue to do so for billions more years into the future. The Milky Way's galactic disk is thought to have formed around 8.8 billion years ago, though its age is not known exactly. The Sun, however, has been precisely dated to be about 4.6 billion years old. Around 9.8 billion years after the Big Bang, the universe started behaving differently for the third time in its history. In the beginning, radiation, like photons and neutrinos, dominated the universe's behavior for the first 47,000 years. Then, for about 370,000 years, matter took over. During this time, the universe's expansion slowed down because gravity started to counteract the initial burst of outward motion. But something changed around 9.8 billion years after the Big Bang. Instead of slowing down, the universe's expansion started to speed up again. Scientists don't know for sure why this happened, but most agree that it's due to a mysterious force called dark energy. The term dark here means that we can't see it directly, but scientists can tell it's there by studying the way it affects the universe's gravity. Dark energy is now believed to make up about 68.3% of the universe's total mass and energy, making it the largest known component of the universe. Research is still ongoing to understand this strange and powerful force. Dark energy is thought to behave like a constant force throughout space, similar to an invisible field that stretches across the entire universe. Unlike gravity, which weakens over time as the universe grows, this mysterious energy doesn't lose its strength. In fact, it continues to have an impact even as the universe expands. While matter and gravity have a noticeable influence in the early stages of the universe, their effects fade away as space keeps growing. At first, we observe that distant objects in space appear to move away from each other as the universe stretches, but over time, their rate of separation slows down. However, this deceleration becomes less and less noticeable as the universe gets bigger and more spread out. Eventually, the force of dark energy, pushing things apart, overpowers gravity's pull, which is trying to bring things closer together. Instead of slowing down and possibly reversing direction, as gravity would suggest, around 9.8 billion years after the Big Bang, the expansion of space begins to speed up, and this acceleration continues to increase over time. There are different ideas about how the universe will evolve in the far future. Which scenario plays out depends on key factors, like the exact values of certain constants in physics, the possibility of protons, the building blocks of atoms, breaking down, and the energy present in empty space. There are also deeper laws of nature beyond what we currently understand in the standard model of physics. If the universe keeps expanding and maintains its current rate of change, one day, almost all galaxies except the ones closest to us will be pushed far away. The speed of space's expansion will be so great that the only galaxies we will be able to observe are those that are within our own local group, held together by gravity. Over extremely long periods, trillions of years from now, the era of star formation will come to an end. New stars will stop forming, and even the oldest stars will burn out and die. After this, the universe will become much colder, with all objects eventually cooling down. They will break apart into their most basic particles, eventually decaying into subatomic pieces and faint energy, like low-energy photons, through various unknown processes. On these timescales, which stretch across many trillions of years, strange and rare events could occur, phenomena that we can't even begin to predict on shorter timescales. For example, black holes, which are known to be incredibly stable, might seem to vanish almost instantly. Some quantum events, which are extremely unlikely to happen within the lifetime of a human or even a star, could become more common over these vast stretches of time. In this distant future, even the most improbable occurrences, things that might happen only once every trillion years, could happen over and over again, changing the state of the universe in ways we can't yet imagine. As we journey deeper into the origins of our universe, we step into the bizarre and mind-bending world of quantum mechanics. Here, the very concept of nothingness is turned on its head. What we once thought of as empty space, completely void of matter or energy, is in reality a restless and dynamic place teeming with invisible activity. At the heart of this revelation lies a fascinating concept known as quantum fluctuations, tiny, unpredictable bursts of energy that continuously appear and vanish in the vacuum of space. For centuries, the idea of empty space was taken quite literally. If you removed all matter, light, and energy from a region of space, it was assumed that nothing would remain. However, modern physics has uncovered something astonishing. Empty space isn't truly empty at all. Instead, it's an ever-active, ever-changing sea of energy where particles constantly flicker in and out of existence. This phenomenon is a direct result of the uncertainty principle, a fundamental rule of quantum mechanics proposed by physicist Werner Heisenberg. The uncertainty principle states that we can never know both the exact position and momentum of a particle at the same time. As a result, even in a vacuum, where we expect absolute stillness, tiny fluctuations in energy are always happening. These fluctuations are the building blocks of what we now call quantum foam, an invisible, churning ocean of activity at the smallest scales of reality. The idea that empty space is full of hidden energy first gained solid experimental support in 1947, thanks to Dutch physicists Hendrik Casimir and Dirk Polder. They conducted a groundbreaking experiment that led to the discovery of what is now known as the Casimir effect. In their experiment, they placed two uncharged metal plates very close together inside a vacuum. Classical physics would predict that nothing should happen. However, to their surprise, the plates mysteriously moved toward each other, as if an invisible force were pulling them together. But what was causing this force? The answer lay in quantum fluctuations. The space between the plates was so small that certain quantum energy fluctuations were suppressed, creating an imbalance in pressure between the inside and the outside of the plates. This imbalance created an attractive force, proving that even in a vacuum, something was there, something invisible but undeniably real. The Casimir effect was a stunning revelation because it provided concrete proof that empty space is anything but empty. It confirmed that the vacuum of space itself contains energy, a discovery that reshaped our understanding of physics and reality itself. Now here's where things get even more mind-blowing. If empty space is filled with quantum fluctuations, could these tiny bursts of energy have played a role in the creation of the universe itself? Many scientists believe that they did. According to some of the most compelling theories in cosmology, the universe may have sprung into existence due to quantum fluctuations in a primordial vacuum. Essentially, what we call nothing might have been filled with these energy fluctuations, and under the right conditions, one of these fluctuations could have expanded exponentially, triggering what we now call the Big Bang. This idea aligns with modern quantum field theory and cosmic inflation, which suggests that our universe was born from a quantum event, not from absolute nothingness, but from a state where energy was already bubbling beneath the surface. The discovery of quantum fluctuations challenges our deepest assumptions about the nature of reality. It suggests that even in the vast emptiness of space, there is an invisible, restless energy at work, one that may hold the key to the greatest questions about existence. Could the universe itself be just one of countless fluctuations, emerging and dissolving in an infinite cosmic cycle? Could quantum mechanics reveal deeper layers of reality that we have yet to comprehend? These are the kinds of questions that physicists continue to explore, as each new discovery peels back another layer of the universe's greatest secrets. The idea that something could come from nothing through quantum fluctuations might seem bizarre at first, but it's a vital concept in understanding how the universe works. In the world of quantum field theory, the vacuum isn't just an empty space, it's more like a bubbling, energetic sea of potential. This energy, hidden in what appears to be a void, has the power to suddenly create and destroy particles in an instant. These fleeting particles, known as virtual particles, don't stick around for long, but their brief appearances have real observable effects. One example of this is the Casimir effect, where even the smallest quantum fluctuations can lead to real physical consequences, such as attracting two objects together, even though they aren't physically touching. Now, what makes this idea even more fascinating is that these tiny fluctuations in energy can pack a huge punch, especially at a microscopic scale. Even though these fluctuations are incredibly small, they can have a profound impact over time. For example, in the early stages of the universe, just moments after the Big Bang, quantum fluctuations might have played a key role in shaping everything we see today. Imagine right after the Big Bang, the universe was in a state of extreme heat and energy. At this time, quantum fluctuations could have acted like tiny seeds, planted in the very fabric of the cosmos. These seeds weren't noticeable at first, but they were vital. As the universe expanded, these fluctuations spread out over vast distances, creating tiny variations in the density of space. These minute differences would have been too small for us to see at first, but gravity worked its magic, pulling on these small irregularities and gradually turning them into the massive structures we now recognize as galaxies, stars, and even the enormous cosmic web that stretches across the universe. The theory of cosmic inflation supports this idea. Cosmic inflation suggests that the universe expanded rapidly, faster than anything we can imagine, just moments after the Big Bang. During this incredibly brief but intense period of expansion, quantum fluctuations would have been stretched across vast regions of space. These fluctuations left behind tiny variations in density, which, over time, grew into the stars, galaxies, and clusters that form the intricate structure of the universe. So, what does this all mean? In essence, quantum fluctuations are not just random and insignificant events. They may be the very mechanism that allowed the universe to grow from a nearly featureless, uniform state into the vast, structured cosmos we observe today. The seemingly random and microscopic fluctuations in the quantum field set the stage for the formation of everything around us, from galaxies to planets to life itself. But the story gets even deeper. Some scientists propose that the entire universe could have emerged from a quantum fluctuation. Imagine this: the universe didn't need a pre-existing cause or creator to come into existence. Instead, it might have arisen from the quantum vacuum itself. As we've learned, the quantum vacuum isn't empty, it's full of energy, with the potential for spontaneous creation. This suggests that the universe could have popped into existence from nothing, no big bang from a pre-existing state, but a sudden burst of energy and matter created from the fluctuations within this empty space. This challenges everything we think we know about cause and effect. In traditional thinking, creation requires a cause. Something has to exist for something else to be created. But in the quantum world, the vacuum itself is a place where creation can happen without a clear cause, where particles can come and go in an instant, and under the right conditions, entire universes could be born. It's a mind-bending idea that pushes the boundaries of our understanding of existence. While quantum field theory and the concept of quantum fluctuations provide a fascinating framework for how the universe might have arisen, this theory is still in the early stages of exploration. There are many unresolved questions about how exactly these fluctuations could lead to the universe we see today. The details of how such an event could occur are complex and remain a mystery, but the idea that the universe could have come from nothing, driven by the strange but powerful forces at play in the quantum vacuum, offers a radically different view of how the cosmos might have begun. The idea that our universe might have come into existence from a tiny, almost invisible fluctuation in quantum energy is both exciting and mind-boggling. It opens up a fascinating look into the mysterious nature of reality itself. When we dive into these thoughts, we are pulled back into an age-old question that has puzzled philosophers and scientists for centuries. How can something come from nothing? Quantum mechanics, a branch of physics that deals with the behavior of the very smallest particles of matter, gives us one possible answer. It challenges our everyday understanding of the world by suggesting that nothing isn't truly an empty void. Instead, it can be thought of as a rich and active space full of potential, a kind of invisible stage where the tiniest fluctuations are constantly happening. These fluctuations are like the seeds of all things, small and barely detectable, yet capable of growing into something immense, like stars or entire galaxies, under the right conditions. This view of the universe's beginnings transforms our thinking about existence. It's no longer about a singular event that happened a long time ago, but about a continuous cycle of creation and destruction happening all the time in the quantum world. In this world, the line between nothing and something isn't as clear as it seems. These quantum fluctuations show us that even what we think of as empty space can be full of untapped energy, waiting for the right moment to give birth to something new. In this sense, the birth of our universe wasn't a one-time, isolated event. It's a never-ending dance, where every moment holds the potential for something new to emerge. The quantum vacuum, often thought of as an empty void, is actually a bustling, energetic playground where creation is constantly happening. The smallest changes or shifts in energy can spark the formation of entire worlds. So, when we ask the question, how can something come from nothing? We begin to realize that perhaps nothing isn't empty at all. Instead, it's a fertile space where the seeds of all possibilities are always lying in wait, ready to sprout when the time is right. Our solar system, the place we call home, didn't just appear out of nowhere. It had a beginning, a formation, and a past filled with wild chaos, violent crashes, swirling clouds of gas, and explosive energy. Billions of years ago, what we now know as our solar system was born from the remains of long-dead stars. Shaped by the powerful forces of gravity and the passage of time, this once chaotic mess eventually settled into something extraordinary. The sun ignited, planets began to form, and Earth, one of those planets, became the birthplace of life. Let's take a deeper dive into how our solar system came into being, how the planets were created, and why Earth is so perfectly suited for life. We'll also look at the theories that help us understand how planetary systems like ours form across the universe. Around 4.6 billion years ago, our solar system was just a huge cloud of gas and dust. This cloud, known as a solar nebula, was the leftover material from the explosion of a massive star. For a long time, this cloud drifted quietly through space, unremarkable and still. But then, something dramatic happened. A nearby supernova, the explosion of a massive star, sent shockwaves through the nebula, causing it to collapse under its own gravity. As the cloud collapsed, it started to spin faster and faster. The faster it spun, the more it flattened out into a disc shape, with most of the material gathering at the center. Over time, the gas and dust in this spinning disk began to stick together, clumping into small pieces that would become the building blocks of planets and moons. But something even more spectacular was happening in the center of this swirling cloud. As the gas piled up and compressed under its own weight, it became hotter and hotter. Eventually, the heat and pressure were so intense that a nuclear reaction sparked, igniting the birth of our sun. The sun's birth was the spark that set everything in motion. Its immense gravity started pulling in more gas and dust, and over millions of years, this material clumped together to form planetesimals, small rocky objects that would later grow into full-fledged planets. However, the early solar system wasn't calm. It was a wild, violent place where planetesimals constantly collided, merging, smashing into pieces, or sometimes combining to form even larger bodies. Eventually, 4 small rocky planets, Mercury, Venus, Earth, and Mars, formed close to the Sun. Farther out, the gas giants like Jupiter and Saturn and the icy giants Uranus and Neptune began to take shape. It was a chaotic, messy beginning that eventually led to the solar system we know today. The 4 inner planets, Mercury, Venus, Earth, and Mars, formed from heavier elements that remained near the Sun after the lighter gases were swept away by solar winds. These planets are mostly made of rock and metal, and their creation was a slow and often violent process. Over millions of years, tiny planetesimals, small rocky or icy objects, collided and stuck together, building up the planets bit by bit. Each crash added more mass, slowly growing the planets. As time passed, these rocky planets developed solid surfaces and atmospheres, but they followed very different paths. Venus and Mars, for example, became worlds that were very different from Earth. However, Earth was on a special course, slowly becoming a unique planet with the perfect conditions for life. Farther out in the solar system, beyond what's known as the frost line, the point where temperatures were low enough for gases like water, methane, and ammonia to freeze into solid ice, the gas giants began to take shape. Jupiter, Saturn, Uranus, and Neptune all started as rocky cores, but their massive size allowed them to capture huge amounts of gas from the solar nebula, the cloud of gas and dust left after the sun formed. This allowed them to grow into the giant planets we know today. Jupiter, being the largest of them all, grew so big that it may have stopped other planets from forming farther out in the solar system. Its enormous gravity also changed the orbits of nearby objects, influencing the structure of the entire solar system. While the creation of these massive gas giants was impressive, something even more extraordinary was happening closer to the Sun. Earth was becoming a planet like no other. Of all the planets in our solar system, Earth is truly unique. It is the only one known to support life, and it has been our home for billions of years. But what makes Earth so special? Why is it the only planet, as far as we know, that can host life? The secret to Earth's uniqueness lies in a combination of factors that have come together in just the right way. Earth's distance from the Sun, its atmosphere, its magnetic field, and the presence of water all contribute to making Earth the perfect environment for life. One of the most crucial factors is Earth's position in what is called the habitable zone. This is the region around a star where the temperature is just right to allow liquid water to exist. The right amount of warmth, not too hot or too cold, makes it possible for life to thrive on Earth, setting it apart from all the other planets in the solar system. Earth's journey through space is truly fascinating. It orbits the Sun at an average distance of about 93 million miles, a perfect location often called the Goldilocks zone. This means it's not too close to the Sun, where everything would be scorched, nor too far, where everything would freeze. Instead, it's just right for liquid water to exist. Liquid water is essential for life as we know it, and Earth's perfect distance from the Sun makes this possible. The importance of liquid water cannot be overstated. Planets like Venus, which are too close to the Sun, have intense heat, causing water to evaporate into the atmosphere, leaving the planet dry and inhospitable. On the other hand, Mars is farther from the Sun, making it too cold for liquid water to remain. Water on Mars would freeze, creating a hostile environment for life. But on Earth, water can exist in all 3 forms: liquid, solid, and gas. This ability allows Earth to create an environment where life can thrive in countless ways. Another critical factor in Earth's habitability is its atmosphere. The atmosphere acts like a blanket, wrapping the planet in layers of gases that serve two vital functions: protecting Earth from harmful radiation and helping regulate the temperature. This protective layer keeps us safe from the dangerous rays and particles that constantly bombard space. Without it, Earth would be exposed to the harsh conditions of space, and life would not be able to survive. Along with the atmosphere, Earth also has a magnetic field, which plays a key role in protecting the planet from solar radiation. The magnetic field is created by the movement of molten iron in the planet's core. This field acts like a shield, deflecting harmful solar winds that could strip away Earth's atmosphere. Without this magnetic shield, Earth would face similar conditions to Mars, where the atmosphere would slowly disappear and life would be impossible. Perhaps one of the most defining features of Earth is the presence of water. Known as the blue planet, because over 70% of its surface is covered by oceans, Earth is the only planet in our solar system where liquid water exists in such abundance. Water is vital for all known forms of life, from the tiniest bacteria to the largest animals. It sustains life, provides nutrients, and helps regulate Earth's temperature, making it essential for life to flourish. Earth's habitability is also shaped by its geological activity. The movement of Earth's tectonic plates plays a crucial role in maintaining the planet's stability. These plates are constantly shifting, causing the recycling of nutrients and regulating Earth's temperature. This process, known as plate tectonics, helps ensure that Earth's long-term climate remains stable. It's this stability that has allowed life to thrive for billions of years. Plate tectonics also creates mountain ranges, earthquakes, and volcanic activity, all of which contribute to the dynamic nature of the planet. But how did Earth and the other planets come into being in the first place? What led to their formation, and why did Earth end up in such an ideal location for life? To understand this, we need to look at the theories of planetary formation, which explain how the planets were born from the dust and gas of the early solar system. The formation of planets is a fascinating and complicated process that has intrigued scientists for hundreds of years. Over time, our understanding of how planets come to be has grown significantly. This is thanks to advancements in technology, such as powerful telescopes that allow us to observe other planetary systems, and to sophisticated computer simulations that model the process of planet formation. But despite all we've learned, the question still remains: how exactly do planets form from the dust and gas in a nebula? There are several theories that attempt to explain this, but the most widely accepted one is called the nebula hypothesis. This theory gives us a clear picture of how planets are formed from the leftover materials around a newly born star. The nebula hypothesis suggests that when a star is born, it is surrounded by a cloud of gas and dust. This cloud, or nebula, is made up of leftover materials from the star's formation. The key idea is that planets begin to form from the gas and dust that make up this nebula. The process starts with a rotating disk of gas and dust, known as a protoplanetary disk, surrounding the young star. As this material orbits the star, small particles of dust and ice start to collide with one another. These tiny particles stick together, creating larger chunks called planetesimals. These planetesimals are the building blocks of planets. Over millions of years, these planetesimals continue to collide and merge, gradually growing larger and larger. Some of them become even bigger, forming what we call protoplanets, early versions of planets. Eventually, these protoplanets grow large enough to be called full-fledged planets. This process of growing by sticking together smaller particles is known as accretion. It's what explains how rocky planets like Earth and Mars formed close to the Sun, while gas giants like Jupiter and Saturn formed farther out, where there was more gas available. The formation of gas giants may have been a little different from that of rocky planets. For gas giants like Jupiter and Saturn, the process started with the formation of a solid core made of rocks and ice. Once these cores became large enough, they could pull in enormous amounts of gas from the surrounding nebulae, growing into massive planets with thick atmospheres. What's particularly fascinating about this process is that it shows how the different types of planets in our solar system ended up in their current positions. Rocky planets like Earth and Mars formed in the warmer inner part of the solar system, where there was less gas but more solid material to build from. Farther out, in the colder outer regions, gas giants like Jupiter and Saturn could form because they had access to more gas, which allowed them to grow much larger. Over billions of years, the process of accretion continued, shaping the planets and their moons. The leftover gas and dust didn't just form planets, though. It also created comets, asteroids, and other small objects that we still find in the solar system today. The theory of core accretion provides one way to explain how gas giants like Jupiter and Saturn came into being. According to this theory, these massive planets started as large, rocky cores. Over time, these cores pulled in enormous amounts of gas from the surrounding space, which then formed thick, dense atmospheres around them. This process takes time and works best for planets that form far from their stars, where there's more gas available. Essentially, the further a planet forms from its star, the more gas it can gather, helping it grow into the gas giants we see today. Another theory called disk instability presents a different idea. This theory suggests that gas giants could form much more quickly. Instead of slowly gathering gas like in the core accretion model, gas giants might form by the collapse of gas in the dense regions of a disk of gas around a young star. This collapse would cause massive gas planets to form much faster. This theory helps explain how gas giants like Jupiter could have formed early enough to prevent the solar wind from blowing away the gas that surrounded the young solar system. Today, scientists can use powerful telescopes to observe the birth of planets in other distant star systems. Instruments like the Atacama Large Millimeter Submillimeter Array and the James Webb Space Telescope give us a closer look at how planets are forming in other parts of the universe. These telescopes have confirmed that planets are being created in very similar ways all over the cosmos. They observe protoplanetary disks, clouds of gas and dust swirling around young stars. As these clouds spin, planetesimals, small building blocks of planets, collide and merge to form planets, just like they did in our own solar system. This means that the way our solar system formed isn't as unique as we once thought. It's part of a much larger process happening throughout the universe. The birth of our solar system was an incredible journey. It started with chaos, a swirling cloud of gas and dust. Over time, this cloud collapsed, leading to the fiery formation of the sun. Meanwhile, violent collisions took place among the particles, and these collisions eventually led to the formation of planets. The process was slow, but over billions of years, the planets settled into their orbits. Each planet is unique, shaped by powerful forces like gravity, gas, and time. Earth, in particular, emerged as a special planet, with the perfect conditions that allowed life to flourish. Now, living on Earth, we are part of this cosmic story. Our planet formed through the same forces that shaped the rest of our solar system and continue to shape planets in other star systems. For as long as people have looked up at the night sky, a big question has always lingered. Are we alone? Is Earth the only place in the vast universe where life can thrive? Or could there be other planets far away from us, where life exists or has taken root? This mystery has intrigued philosophers, scientists, and dreamers alike for centuries. It's a question that challenges everything we know about the universe, pushing the boundaries of science and imagination. Now, with powerful new telescopes and cutting-edge technologies, we are closer than ever to answering this age-old question. The search for extraterrestrial life, life that exists beyond our Earth, is one of the most thrilling and profound pursuits in all of science. It's a quest that takes us on a journey to distant exoplanets, planets that orbit stars far away from our own solar system, and deep into the unknown parts of our very own solar system. Along the way, we are forced to rethink what life even is and what it means to be alive. In this fascinating exploration, scientists are diving into what makes a planet capable of supporting life. They are studying the specific conditions needed for life to exist and thrive. Using advanced tools, formulas, and equations, they try to estimate the chances of discovering other civilizations out there in the universe. They are also searching for signals from intelligent beings far out in space, hoping to find some proof that we are not the only ones here. On Earth, we live on a planet filled with life in every form imaginable, from the tiniest single-celled bacteria to the largest, most complex mammals. But what makes Earth so special, so full of life? The answer lies in the conditions that make our world habitable. Scientists believe that if we can understand what makes life possible here, we might be able to identify other planets where life could exist. One of the most crucial ingredients for life as we know it is liquid water. Water is absolutely essential for all forms of life on Earth. It acts as a solvent, helping to break down substances and enabling chemical reactions that are necessary for life. Water also helps transport nutrients, keeps temperatures stable, and supports the structures inside cells. It's hard to imagine life without water. It's the key to the biological processes that sustain us. But why does Earth have liquid water? This is because our planet is in a special region around the Sun called the habitable zone. This is the area where temperatures are just right for water to remain in liquid form, not too hot and not too cold. Planets that are too close to the Sun, like Venus, are too hot, causing any water on their surface to evaporate. On the other hand, planets that are too far away from their stars, like Mars, are too cold, causing water to freeze. But here on Earth, we have the perfect conditions to keep water in liquid form, which makes our planet the ideal place for life to exist. In addition to liquid water, life also requires an energy source. On Earth, most life forms rely on energy from the sun. Plants capture this energy through photosynthesis, while animals indirectly depend on it by eating plants or other animals. The sun's energy drives everything from the smallest plant to the largest predator, fueling the cycles that keep life going on Earth. However, scientists have discovered that life doesn't always need sunlight to survive. Deep beneath the oceans, far from the sun's rays, life still flourishes. Around hydrothermal vents, cracks in the Earth's seafloor that release heat and chemicals from the planet's core, strange organisms thrive. These creatures don't rely on the sun's energy at all. Instead, they use the heat and chemicals from these vents as their energy source, showing that life can exist in extreme conditions that are completely different from the ones we see on the surface of the Earth. This discovery has dramatically changed how we think about the potential for life elsewhere in the universe. If life can survive in these harsh, deep ocean environments on Earth, it opens up new possibilities for life on other planets or moons. Could there be places out there in space where life could exist under similar extreme conditions without sunlight? Perhaps moons like Europa, one of Jupiter's moons, or Enceladus, a moon of Saturn, have the right ingredients, water, heat, and chemicals, for life to thrive in their icy oceans beneath the surface. Life, as we know it, depends on many factors, but one of the most crucial is a stable environment. For life to develop and evolve, a planet must be able to sustain conditions for millions or even billions of years. Think of it like planting a tree. If the soil, sunlight, and water are all unstable, the tree won't grow. Likewise, Earth has the right conditions for life to thrive, but what about other planets? Can they also support life? One of the most important things Earth offers life is its atmosphere. This invisible layer around our planet plays several key roles. It protects us from dangerous radiation coming from outer space. It helps keep temperatures within a range that living creatures can handle, and it also keeps harmful solar winds at bay. Without our atmosphere, Earth would be a cold, lifeless rock, bombarded by radiation, where life would struggle to survive. Now, think about what it would take for another planet to support life. For a planet to have the right conditions, it would need an atmosphere to protect against cosmic radiation, a way to control the temperature, and a magnetic field to shield it from harsh solar winds. These are the same features Earth has, and without them, a planet would be exposed to dangerous radiation, making it incredibly hard for life to survive. So, the big question is, how likely is it that other planets out there in space have these same protective conditions that Earth has? Are there other places in the universe where life could develop just like it did on Earth? To explore this question, scientists turn to something known as the Drake equation, named after astronomer Frank Drake, who came up with it in 1961. This equation was designed to estimate how many civilizations in our galaxy might be capable of communicating with us. It's a way to think about the many factors that play a role in the search for extraterrestrial life. The Drake equation is simple in concept, but covers a lot of ground. It helps break down the big question into smaller, more manageable parts, each of which addresses a different factor that might influence whether intelligent life can emerge elsewhere in the universe. Each part of the equation asks a big question. For example, how many stars in the galaxy have planets? Out of those, how many have planets where life could potentially begin? Of those planets with life, how many will develop intelligent life? And once intelligent life exists, how many civilizations will develop the technology to send signals across vast distances in space? The Drake equation isn't meant to give us a clear, exact answer. It's more of a tool to guide our thinking and help us understand the many variables that could determine whether other intelligent life exists. It's a way to organize our search for extraterrestrial life by considering all the factors that could influence it. Even with all these considerations, there's one big question that still hangs over everything. If life is common in the universe, why haven't we heard from anyone yet? This is often called the Fermi paradox. We know that life could potentially exist out there, but the more we look, the less we find. It's a mystery that continues to puzzle scientists and spark the imaginations of dreamers around the world. So as we search the stars, we keep wondering, where is everybody? Why haven't we found evidence of other civilizations if life could be so common? In 1950, the famous physicist Enrico Fermi raised a simple yet profound question. Where is everybody? Fermi was referring to the idea that if the universe is so incredibly vast, and if intelligent life is common, then why haven't we found any signs of extraterrestrial civilizations? This thought-provoking question became known as the Fermi paradox, which highlights the strange contradiction between the high likelihood of other intelligent life forms existing in the universe and the total lack of evidence for them. The paradox essentially asks why, with so many stars and planets scattered across the universe and the growing possibility that some of them might harbor intelligent life, we haven't encountered any signals or signs of these civilizations. The universe is so enormous and the odds seem so high that life should exist elsewhere, yet our search has turned up nothing so far. It's a mystery that has puzzled scientists for decades. There are many possible explanations for the Fermi paradox, but none that are definitively proven. One idea is that intelligent civilizations could be extremely rare, making them hard to detect. Maybe life exists, but it hasn't evolved to the point of developing advanced technologies like ours, which would allow for long-distance communication or space travel. Another possibility is that intelligent civilizations may simply not last long enough to develop such technologies. They could self-destruct through war, environmental collapse, or other catastrophic events before they are able to send out signals or explore the stars. Other scientists have proposed that the civilizations we are searching for might be so far away that their signals have not yet reached us, or perhaps the distances between us and them are just too vast for us to detect. It's also possible that these civilizations are actively avoiding contact with us, whether for safety, ethical reasons, or because they have no interest in interacting with less advanced species like ours. Despite these challenges, our search for extraterrestrial life continues, driven by the hope that one day we will find evidence of another civilization, or at least discover proof that life exists beyond Earth. The potential discovery of intelligent extraterrestrial life would undoubtedly be one of the most groundbreaking moments in human history. It would change everything we know about our place in the cosmos and our understanding of life itself. Even though we have not yet found any aliens, the journey itself has led to fascinating discoveries about the universe and our own existence. The search for alien life is now a global endeavor, with scientists and astronomers from all over the world working together and using some of the most advanced technologies available to scan the skies. We use enormous radio telescopes to listen for signals that could be sent by intelligent life forms. These radio telescopes are designed to detect very specific types of signals called narrowband radio signals. These are signals that are so precise and focused that they would be unlikely to come from natural sources like stars or planets. Instead, they could be the result of an advanced technological civilization trying to communicate across space. Although no confirmed signals have been detected yet, scientists are hopeful, and the search continues, using more sensitive equipment that allows them to scan broader regions of the sky, improving the chances of finding something significant. In addition to the search for signals, another major effort is the search for exoplanets, planets that orbit stars outside of our solar system. Missions like Kepler and TESS have helped us discover thousands of these planets, revealing that planets are far more common in the universe than we ever imagined. In fact, there are likely more planets than there are stars in our galaxy alone. This discovery has led to exciting possibilities. Some of these exoplanets are located in what is known as the habitable zone, which is the area around a star where conditions might be just right for liquid water to exist. Since we know that water is essential for life as we know it, these planets are considered prime candidates for supporting life. With each new discovery, scientists are getting closer to identifying a planet that might have the right conditions to support life. But even as we look further into the farthest reaches of space, there are also intriguing possibilities much closer to home. There are moons in our own solar system, like those around Jupiter and Saturn, that have environments where life could potentially exist, such as under their icy crusts. These possibilities suggest that we may not have to look only to distant stars to find evidence of life in the universe. Some of the most exciting places where scientists are searching for life are surprisingly close to home, right here in our own solar system. Take, for example, the moons Europa and Enceladus. These moons may seem like frozen, barren worlds at first, but they hold secrets beneath their icy exteriors. Both Europa, which orbits Jupiter, and Enceladus, which orbits Saturn, are covered by thick layers of ice. However, scientists believe that underneath this icy surface, there are vast hidden oceans of liquid water, oceans that might be perfect for supporting life. Water is crucial for life as we know it, and these subsurface oceans could provide the right conditions for living organisms to survive, even in extreme environments. Europa, in particular, has long been a focus for researchers. NASA's upcoming Europa Clipper mission is set to launch in the near future and will explore the moon in detail. The mission aims to search for signs of life beneath Europa's icy shell by studying its ocean, ice, and other surface features. Scientists are especially curious to learn whether the conditions on Europa could resemble those that support life here on Earth, such as the deep-sea vents where strange creatures thrive far from the sun. Enceladus, too, is an intriguing target in the search for life. In 2005, NASA's Cassini spacecraft discovered that the moon releases plumes of water vapor from its icy surface. These plumes suggest that there is a liquid ocean beneath the ice, and they could contain chemicals necessary for life. If microbes are present in these hidden oceans, it would be a huge step in proving that life could exist beyond our planet. What makes these moons so fascinating is that they might help us understand how life could survive in harsh, distant environments. If life can thrive in the deep oceans of Europa or Enceladus, it could change our thinking about where life might exist in other parts of the universe. These discoveries might even help us imagine new possibilities for where life could be hiding, perhaps on other icy moons or planets we haven't even discovered yet. The quest to find life beyond Earth is one of the most profound and exciting challenges humanity has ever faced. It makes us question everything we know about life, the universe, and our place within it. Are we truly the only intelligent beings in the universe? Or is there something or someone else out there waiting to be discovered? Every new discovery, whether it's the detection of a distant planet, an unusual signal from space, or the discovery of a hidden ocean beneath the ice, brings us a little closer to answering that age-old question. For almost 14 billion years, the universe has been expanding, evolving, and changing in ways we can only begin to understand. Stars have been born, galaxies have collided, and planets like Earth have formed, creating the conditions for life to emerge. Yet, as we look deeper into the cosmos, we realize that nothing lasts forever, not even the universe itself. This incredible, vast universe that has given rise to everything we know is, in fact, on a journey toward its own end. As scientists peer further into the depths of space, one profound question keeps echoing: how will the universe end? The answer is tied to the forces that shape the cosmos: gravity, dark matter, and the mysterious force known as dark energy. Each of these plays a crucial role in determining the ultimate fate of the universe. In this exploration, we will dive into some of the most compelling theories that attempt to predict how it all might come to an end. From a slow, cold death in the Big Freeze to the violent, catastrophic disintegration of the Big Rip, or even a potential rebirth through the Big Crunch. These possibilities offer us a glimpse into the far future of everything we know, raising a number of questions about the stars, galaxies, and black holes that light up the universe today. Will they survive as time marches on, or will they meet their cosmic end? The universe has been expanding ever since the Big Bang, and this expansion continues to this day. But how it will all end depends on the balance between two powerful forces: gravity and dark energy. Gravity, the force that pulls things together, and dark energy, the mysterious force that pushes things apart, are in a constant battle for dominance. Dark energy is particularly enigmatic. It's the force behind the accelerated expansion of the universe, but scientists are still unsure of what it truly is or how it works. Despite the many mysteries surrounding dark energy, it is crucial to understanding the fate of the cosmos. It holds the key to answering that central question: how will the universe ultimately end? Scientists have developed several theories about how the universe might meet its end, each shaped by how gravity, dark energy, and the fundamental laws of physics interact. Let's explore these theories one by one. One of the most widely accepted theories is known as the Big Freeze, or the heat death of the universe. In this scenario, dark energy continues to push the universe apart, causing it to expand at an ever-accelerating rate. As galaxies move farther away from each other, the universe grows colder, emptier, and more isolated. Over billions of years, stars will burn through their fuel, one by one, and eventually die. Some will leave behind remnants like white dwarfs, neutron stars, and black holes. But with no new stars being born, galaxies will gradually become dimmer and dimmer. In time, the universe will become a cold, dark, and empty place. The last remaining stars may continue to burn for trillions of years, but eventually, even they will run out of fuel. This dark, silent future is known as the heat death. It's a slow, quiet end to the universe, a cosmic big freeze. In this scenario, entropy or disorder will reach its maximum, and all energy will be evenly spread out across the universe. With no energy left to fuel life or any processes, the universe will essentially be in a state of eternal, frozen stillness. However, there are other more dramatic possibilities for how the universe could end, especially if dark energy behaves in a different way. One such theory is known as the Big Rip. In this scenario, dark energy doesn't just drive the universe's expansion, it accelerates it at an ever-increasing rate. Over time, the force of dark energy becomes so strong that it starts pulling apart not only galaxies, but stars, planets, and even atoms themselves. At first, the effects of the Big Rip would be subtle. Galaxies would move farther apart, just as they do in the Big Freeze. But eventually, the expansion would accelerate so rapidly that the very fabric of space and time would begin to unravel. First, galaxies would break apart, then stars would be ripped from their homes in galaxies. Planets would be torn away from their stars, and eventually, the force of dark energy would become so powerful that even atoms and subatomic particles would be torn asunder. The universe would end in a violent, catastrophic event, with space itself collapsing into nothingness. The Big Rip would be a tragic and violent end where everything, the very building blocks of matter, would be pulled apart. Whether this theory becomes a reality depends on the properties of dark energy. If it continues to grow stronger over time, the universe might indeed end in this violent cosmic disintegration. But what if the universe doesn't expand forever? What if gravity wins in the end? In the Big Crunch scenario, gravity begins to overpower dark energy, slowing down the universe's expansion and eventually reversing it. Over billions of years, the galaxies, stars, and planets that had been drifting apart would start to come back together. The force of gravity would draw them closer and closer, causing galaxies to collide, stars to merge, and the universe to shrink. As the universe collapses, it becomes increasingly dense and hot. This process would continue until everything, galaxies, stars, planets, would be crushed together into a single point, much like the singularity from which the Big Bang originated. This singularity would be a moment of infinite density and heat, possibly leading to the birth of a new universe. Some scientists speculate that this Big Crunch could trigger another Big Bang, starting the cycle of creation and destruction all over again. In this view, the universe would experience an endless loop of expansion and collapse, a cosmic recycle that continues over eternity. This idea of how the universe might end is incredibly interesting, but it's still just a theory. Right now, scientists are seeing that the universe's expansion is actually speeding up, not slowing down. There are different ideas about how the universe might eventually end: the Big Freeze, the Big Rip, and the Big Crunch. Each of these ideas gives us a different picture of what could happen, but they all depend on one major thing: the mysterious force called dark energy. The big question is, what will happen with dark energy? Will it continue to make the universe expand faster? Will it grow stronger as time goes on? Or will gravity eventually pull everything back together, making the universe shrink again? Right now, no one knows for sure. The future of the universe is still uncertain, but we know that dark energy will play a huge role in determining how everything ends. Astronomers first discovered that the universe was expanding, and they thought that gravity would eventually slow it down. But then, in 1998, something unexpected happened. Scientists found out that the universe wasn't just expanding, it was expanding faster and faster. This discovery led to the idea of dark energy, a mysterious force that seems to be driving this faster expansion. In fact, dark energy is believed to make up about 68% of the universe. But even though we know it's there, we still don't know exactly what it is. Some scientists think that dark energy could be a constant force called a cosmological constant. This would mean that dark energy is a fixed energy that exists everywhere in empty space. Others think that dark energy could be more dynamic, meaning it changes over time. It could become stronger or weaker as the universe evolves. If dark energy is a cosmological constant, the universe will keep expanding forever, but it will gradually slow down and grow colder, leading to a slow and cold death known as the Big Freeze. On the other hand, if dark energy is a force that gets stronger over time, the universe could end in a much more dramatic way, tearing itself apart in an event known as the Big Rip. Figuring out what dark energy actually is remains one of the biggest challenges in modern science. The answer to this mystery could help us understand what the future of the universe looks like and how it will end. While all of this has to do with the distant future, it's also important to think about how individual stars, galaxies, and black holes will come to their own ends long before the universe itself finishes its journey. Over the next trillions of years, these cosmic objects will undergo major changes, and they'll all eventually meet their own fate. Understanding how they will evolve is key to understanding the universe's future. Stars, those brilliant lights that illuminate the vastness of the universe, have a limited lifespan, much like all living things. Our own sun, for example, is already about 4.6 billion years old, and it will continue to burn for another 5 billion years or so before it runs out of fuel. But what happens to stars when they eventually reach the end of their lives? How do they evolve and disappear over time? Stars come in all sizes, and their fates are determined by their mass. The smaller stars, such as red dwarfs, burn their fuel slowly, which allows them to live for incredibly long periods, trillions of years in fact. These stars will be the last to flicker out in the universe, hanging on longer than anything else. Imagine a small, quiet star slowly glowing in the vast blackness of space, lasting far beyond the current age of the universe, a steady beacon against the cold emptiness. On the other hand, larger stars like our sun will go through a dramatic transformation before they die. As they run out of fuel, they expand into enormous red giants, growing many times larger than their original size. In this stage, they will shed their outer layers into space, creating a beautiful, glowing nebula. What remains at the core is a white dwarf, an incredibly dense, small remnant of the star that will slowly cool down over billions of years. It's a quiet and lonely existence for the white dwarf, slowly losing its warmth as time marches on. But the most massive stars are the real showstoppers. When they reach the end of their lives, they don't just fade away. They explode in a brilliant event known as a supernova. This explosion is so powerful that it can outshine entire galaxies for a short period of time. What's left after this massive explosion can be one of two things: a neutron star or a black hole. A neutron star is an incredibly dense remnant where the core of the star has collapsed into a tiny, supercompressed sphere. A black hole, on the other hand, is one of the most mysterious and intriguing objects in the universe. It's a region of space where gravity is so strong that nothing, no light, no matter, can escape its pull. But even these massive remnants are not immune to time. Over the course of trillions of years, everything in the universe, even black holes, will eventually fade away. Black holes may seem invincible because of their enormous gravity, but they slowly lose mass over time due to a process known as Hawking radiation. This radiation is extremely weak, which means it would take far longer than the entire current age of the universe for black holes to evaporate. But eventually, after unimaginable amounts of time, trillions upon trillions of years, even the most massive black holes will disappear, leaving behind nothing but empty space. As the universe continues to expand, galaxies will drift farther and farther apart. In the distant future, galaxies like our Milky Way and its closest neighbor Andromeda will merge together to form even larger and more massive galaxies. This process, however, won't last forever. Dark energy, a mysterious force driving the expansion of the universe, will continue to push galaxies farther apart. These large galaxies will eventually become isolated, and star formation will come to a halt. The gas needed to form new stars will be used up, and without new stars to shine, galaxies will grow darker and darker. As the stars run out of fuel and no new stars are born, galaxies will fade into a deep, eternal darkness. The universe will become a cold, empty place, filled only with the remnants of stars that once shone so brightly. The galaxies will drift in isolation, their once vibrant lights completely extinguished. The universe is an extraordinary place, vast, beautiful, and full of mysteries. It stretches beyond what we can even imagine, leaving us in awe of its grandeur and complexity. But like everything in existence, the universe too has its beginning and its end. While we are witnessing it in all its glory today, we are also aware that this beauty is not everlasting. Whether the universe fades into a cold, dark eternity, known as the Big Freeze, violently tears itself apart, the Big Rip, or collapses in on itself, eventually rebirthing into something new, the Big Crunch, one day it will come to a close. The universe's story, like all stories, will have a final chapter. Nothing lasts forever. The stars that light up the night sky will burn out. Black holes will eventually disappear as they evaporate, and even the mighty galaxies we observe today will one day vanish. But for now, we are lucky. We live in an extraordinary moment, a brief flicker in the timeline of the universe, where we can witness it in its prime, filled with light, life, and wonder. The ultimate fate of the universe, however, remains one of the most profound mysteries of all. We do not yet know whether the end will be a slow decay, a dramatic collapse, or some other unimaginable fate. But one thing is clear: the universe's story is far from over. At the heart of many of these philosophical discussions is the principle of causality, the idea that everything we observe must have a cause. In our everyday lives, everything seems to have an explanation. A tree grows because a seed was planted. A star shines because nuclear fusion is taking place at its core. But when we turn our attention to the origin of the universe itself, we confront a deep mystery. What caused the universe to exist in the first place? Some philosophers and theologians argue that the universe must have a cause that is beyond the physical world. This idea is connected to what is known as the cosmological argument, which posits that the universe cannot simply be self-caused or exist without reason. It must have come from something beyond it. On the other hand, some suggest that the universe might not need a cause at all. Perhaps the universe is simply a brute fact, something that exists without explanation. In the same way that we accept certain physical laws like gravity without always questioning them, maybe the universe just is and doesn't need a cause. Another key philosophical concept is the distinction between contingent and necessary existence. A contingent thing is one that could have been different. Earth, for example, could have failed to exist, or it could have looked very different. Stars, planets, and even galaxies are all contingent. They don't have to exist the way they do. Some philosophers suggest that the universe and the laws that govern it may have been necessary. Others argue that the universe could have easily not existed at all, raising the possibility that there was, at one point, the potential for nothing. These questions lead us to another mind-bending thought. Could the universe have arisen from nothing? This is where science and philosophy begin to collide. Some scientists believe that based on the strange principles of quantum mechanics, the universe might have come into existence from a state of quantum nothingness. In the strange world of quantum physics, particles can appear and disappear, seemingly from nothing. Some suggest that the entire universe could have originated in this way, spontaneously emerging from what seems to be nothing.